Good evening, and welcome to the Sleepy Geographer. This space is made for slowing down at the end of the day, letting the mind drift gently while still being fed something thoughtful and true. Tonight, we're exploring a quiet but powerful idea: how the shape of the Earth itself guides the shape of life. From mountains and rivers to coastlines and deserts, geography sets the stage on which biodiversity performs its endless play. Before we settle into the journey, I'd love to know, where are you listening from tonight? And what time is it there? It's always fascinating to see the little constellation of places this channel reaches, and if you enjoy this calm wander through geography, a like and a subscribe helps more than you'd imagine. Thank you deeply to those of you who are already part of this sleepy, curious corner of the world. I only hope the story isn't so fascinating that it keeps you awake. But then again, if it does, at least your dreams may be filled with rivers, mountains, and the winding paths of life itself. So, let's begin. What hidden patterns of the Earth decide where the world's species live, thrive, or fade away? The world looks alive in patchwork. Forests stop at deserts, rivers bend and split, mountains rise and slice the sky into wet and dry halves. To a tired eye, these might seem like accidents of the landscape, but for life itself, they are the rules of the game. Geography is not just background scenery, it is the architect, the barrier, the corridor, and the caretaker. When a mountain climbs, it draws rain on one side and casts drought on the other. When a river splits, it can either connect creatures or keep them apart. Islands, valleys, caves, coastlines, each is both a gift and a challenge. And over countless ages, species have listened and adapted, shaped by the lay of the land. This journey will move slowly and deliberately, from deep tectonic forces under the crust to the fragile green edges where ecosystems meet. Each chapter will take a single geographic feature: mountains, deserts, islands, rivers, soils, and trace how it writes its own script in biodiversity. To make it easier to follow, we'll often pair the idea with a place: the Andes, the Sahara, the Galapagos, the Amazon. Geography sets the rules, and life, endlessly inventive, plays along. The point is not to rush through facts, but to let them unfold at the pace of the Earth itself, slow, steady, and deeply grounding. By the time we reach the end, the hope is simple: that the land beneath your feet will seem less like inert ground and more like a living author, quietly writing the story of life. So take a slow breath, let the weight of the day fall away, and imagine if you could see the entire planet from above. Would the patterns of life mirror the patterns of land and sea as perfectly as a reflection in still water? Deep beneath your feet, the Earth is never still. It moves so slowly that a lifetime passes without you noticing, yet it is always shifting, always breathing in its own deep rhythm. The continents are not fixed, but ride on restless plates of rock that glide, grind, and collide on a mantle of flowing heat. Over millions of years, these motions carve new landscapes, lift mountains into the sky, and open valleys where lakes collect. It is in this restless choreography that life finds both opportunity and obstacle, and biodiversity takes its cues from the turning of the planet's great geological wheel. When two plates collide, the Earth folds and crumples like a rug pushed against a wall. Out of that upheaval, mountain ranges are born. The Andes in South America are a vast reminder of this process, stretching like a spine along the continent's western edge. They rise because the oceanic Nazca Plate dives beneath the South American plate, driving the crust upward and creating the longest continental mountain chain on Earth. This towering wall does more than decorate the skyline. It shapes wind and water, funnels clouds, and decides who lives where. Moist air blowing from the Amazon basin is pushed up against the Andes' eastern slopes. As it rises, it cools and condenses into rain, feeding some of the richest cloud forests in the world. The air that crests the peaks and tumbles down the western slopes is stripped of its moisture, leaving arid valleys and deserts in its wake. The Atacama Desert, often called the driest place on Earth, owes much of its parched existence to this very process. One set of mountains, one collision of plates, and you have both a rainforest dripping with life and a desert where survival is pared down to the barest essentials. Geography, sculpted by tectonics, dictates the fate of plants, animals, and entire ecosystems. The Andes also create something subtler, gradients of climate stacked like floors in a high-rise. As you ascend, temperature and vegetation change in steady steps. At low altitudes, lush forests dominate, filled with orchids, bromeliads, and monkeys that swing between the branches. Higher up, cooler cloud forests give way to grasslands, and then to windswept puna, where hardy shrubs cling to the soil. Keep climbing, and eventually you reach snowfields and glaciers where few species dare survive. Each band of altitude becomes a different home, encouraging specialization and endemism. Creatures separated by just a few kilometers of slope may as well be worlds apart, cut off by the harsh barriers of cold, thin air and changing vegetation. The Great Rift Valley of East Africa tells another version of the story. Here, the Earth is not folding upward, but pulling apart. Tectonic forces stretch the crust until it thins and splits, creating long, deep valleys flanked by escarpments. Over millions of years, these troughs fill with water, forming great lakes, Tanganyika, Malawi, Turkana, each one a watery universe of its own. The isolation of these basins has been a gift to evolution. In Lake Malawi alone, hundreds of species of cichlid fish have evolved, many found nowhere else on Earth. They have taken on roles as varied as insect eaters, algae grazers, snail crushers, and even scale eaters that nip at the sides of larger fish. This explosion of diversity, what biologists call adaptive radiation, was sparked by nothing more dramatic than a continent stretching apart, letting water pool in the low spots and giving life the canvas it needed to paint in countless colours. Tectonics does not hurry. Plates drift only a few centimetres each year, slower than a fingernail grows. Yet over deep time, those centimetres pile up into mountain chains and split continents. From the perspective of life, these changes are dramatic, even if they unfold at a pace so gradual that no single generation would ever notice. A forest grows and thrives on one side of a range, while a desert tests endurance on the other. Fish evolve into a kaleidoscope of forms in a rift lake while the wider world carries on oblivious. This slow-motion rearranging of the Earth has profound consequences for biodiversity. When continents drift, species are carried with them. South America, for example, was once an isolated island continent. Its marsupials, giant ground sloths and terror birds evolved in splendid solitude. Only when the Isthmus of Panama rose up and joined the land to North America did new waves of animals cross, jaguars, horses, tapirs, reshaping the continent's ecosystems forever. Again, the quiet grinding of plates beneath the ocean rewrote the living script above ground. The humour, if one can call it that, is that tectonics is Earth's most patient storyteller. It spins tales so slowly that even the oldest redwoods or the longest-lived tortoises only glimpse the smallest fraction. If the planet had a lullaby, it would be the groan of rock under pressure, the sigh of continents drifting apart, and the whisper of mountains rising grain by grain. It is a tune so low and long that we humans rarely notice, but all the while life bends to its rhythm. And so beneath our daily landscapes lies the blueprint of diversity. Each ridge, valley and basin traces its origin back to the shifting of plates. Mountains catch clouds and so forests. their rain shadows sow deserts. Valleys collapse into lakes that cradle fish into unique forms. Continents meet and part, ferrying creatures to new homes. What feels permanent beneath our feet is really a canvas forever being redrawn, and life, with patient ingenuity, adapts to every new stroke. In the end, the quiet power of tectonics reminds us that even the most stable-seeming world is in flux. If you listen closely, you can almost hear it. A planet turning in its sleep, the ground humming softly, setting the tempo to which all life must dance. Imagine standing on the equator at noon. The sun is almost directly above, its light falling in a nearly vertical column, warming the ground with extraordinary intensity. Now imagine yourself near the Arctic Circle, where the same sun hangs low on the horizon, spreading its rays across a much broader surface, delivering only a faint fraction of that energy. This simple difference in angle is the great divider of climates, the quiet force behind deserts and rainforests, tundra and savannas. Latitude is more than just a line on a map. It is the invisible script that life follows, setting the pace of seasons, the rhythm of rains, and the boundaries of entire ecosystems. The Earth is round, tilted, and forever spinning. Because of its curvature, sunlight does not strike all places equally. At the equator, energy arrives head-on, concentrated and strong. At higher latitudes, the same beam of sunlight must cover a larger patch of land, like butter spread thin on bread. Less energy means cooler temperatures, longer winters, and shorter growing seasons. This difference in insulation, as geographers call it, is what creates the great gradient of climates from equator to poles. But the story does not end with sunlight alone. Heat stirs the air, and air in motion never sits quietly. Warm air rises at the equator, where intense heating causes massive columns of moisture-laden atmosphere to surge upward. As it climbs, the air cools, releasing torrents of rain. These downpours sustain the lush green belt of tropical rainforest, the Amazon, the Congo, and the jungles of Southeast Asia. After losing its moisture, the now dry air drifts north and south, eventually descending around 30 degrees latitude. This sinking air creates high-pressure zones that suppress rainfall, producing some of the planet's great deserts: the Sahara, the Kalahari, the Arabian sands, and even the deserts of Australia. This repeating circulation, known as Hadley cells, is the great conveyor of climate. It explains why the Earth wears bands of ecosystems like stripes: rainforest at the equator, drylands in the subtropics, temperate forests further on, and boreal forests giving way to tundra at the poles. Stand back far enough, and the pattern is remarkably clear, like rings on a spinning globe, each tied to latitude. Take South America as an example. In the heart of the continent, the Amazon sprawls under the equatorial sun, its trees drawing life from the endless rain. Just a little north, the landscape begins to dry into the llanos of Venezuela, and further still the deserts of the Caribbean coast emerge. A short trip in latitude can mean the difference between a canopy dripping with epiphytes and a scrubland where only the hardiest thorny plants persist. Latitude is destiny, at least when it comes to climate. Contrast the Amazon with the Sahara across the Atlantic. The Sahara's dry heat is also born of latitude, lying right beneath the descending branch of the Hadley cell. Here, rainfall is so scarce that vast stretches of sand and stone dominate, broken only by oases where underground water breaks through. Life here survives on clever adaptations: camels storing fat in their humps rather than water, plants with roots stretching deep to hidden aquifers, and people who learned long ago to read the desert's rhythms. The difference between the Amazon's dripping leaves and the Sahara's sun-baked dunes comes down to the angle of the sun, the rising and sinking of air, and the planet's rotation. Further north, The boreal forest tells another chapter of this latitudinal tale. Stretching across Canada, Scandinavia and Siberia, this biome forms the largest continuous forest on Earth. It thrives where summers are short, winters are long, and the sun never climbs high in the sky. Conifers dominate: spruce, fir, pine, trees that can photosynthesize in cooler temperatures and hold their needles year-round. The animals here, from moose to lynx, are equally attuned to the seasonal pulse. When the brief summer comes, life rushes to take advantage of the long daylight hours, and when the snow returns, survival depends on endurance and stored energy. Seasonality itself is also a child of latitude. Because the Earth is tilted about 23.5 degrees on its axis, sunlight shifts north and south across the year. The closer you live to the poles, the more dramatic the swings. Near the equator, day length barely changes, and plants and animals live in a near-eternal cycle of growth and reproduction. Move toward the mid-latitudes, and the year begins to divide itself. Spring for awakening, summer for abundance, autumn for retreat, and winter for rest. At extreme latitudes, the contrast becomes striking. Endless days of light in summer, endless nights of darkness in winter. Life bends around these seasonal contrasts, timing migration, flowering and hibernation to the turning of the planet. Latitude also dictates productivity. In equatorial forests, year-round sunlight and moisture drive photosynthesis at high levels, producing more plant material than almost anywhere else. This abundance supports immense webs of life, from tiny leafcutter ants to jaguars prowling the shadows. At higher latitudes, where light and warmth arrive only briefly, productivity drops and ecosystems grow simpler. Yet even simplicity holds beauty. Vast herds of caribou tracing ancient paths, flocks of migratory birds timing their arrival to coincide with insect hatches, and hardy lichens covering bare rock. It is tempting to see latitude as a kind of planetary metronome, setting tempo for the entire living world. Near the equator, the beat is fast and constant, pulsing with growth. Toward the poles, the rhythm slows, marked by long pauses and sudden bursts of activity. Every creature, from the tiniest hummingbird to the largest whale, finds its place in this great latitudinal score. And so the angle of the sun and the tilt of the earth quietly dictate the stage on which life unfolds. From equatorial jungles thick with sound to silent snowy forests stretching across continents, latitude draws the boundaries. It is geography at its most fundamental, turning sunlight into seasons, seasons into habitats, and habitats into the diverse forms of life that share this planet. Mountains are the Earth's vertical storytellers, rising suddenly from plains or coasts and stacking climates in layers like a great tiered cake. Walk from the foothills to the summit of a tall range, and you're not just climbing upward, you're passing through worlds. Each few hundred meters of elevation feels like a shift in latitude, as though you were moving from the tropics toward the poles in the space of a single day's hike. This phenomenon is driven by lapse rates, the predictable cooling of air as it rises. For every 1,000 meters gained in height, the air temperature drops by roughly 6.5 degrees Celsius, and that change cascades through everything from soil chemistry to the shapes of leaves. The Andes show this layering with striking clarity. Begin in the steamy Amazonian lowlands, where buttressed trees tower above a forest floor heavy with humidity. Climb a little higher, and the trees become smaller, festooned with orchids, bromeliads, and mosses that cling to every branch. This is the cloud forest, a world perpetually wrapped in mist, where water does not simply fall from the sky, but drifts sideways as fog. Birds like the resplendent quetzal flash through the canopy, while spectacled bears shuffle along the slopes in search of fruit. Higher still, the forest thins into windswept grasslands, known as paramo or puna, where cushion plants hug the ground against the chill and llamas graze under an endless sky. At the very top lie glaciers and scree, realms of stone and ice where only the hardiest mosses and insects endure. This stacked arrangement makes mountains into miniature continents, compressing the journey from rainforest to tundra into a single climb. Because each band is relatively narrow, species often specialize to very tight ranges of elevation. A hummingbird might be adapted to the nectar of flowers that only bloom at a certain altitude, while a frog may breed in streams that tumble from cloud forest into grassland. Move too far up or down, and the conditions change too much. These fine-scale adaptations foster endemism, species found in one mountain range, or even on one slope, and nowhere else. The Eastern Arc Mountains of Tanzania and Kenya are a beautiful example of this isolation. Scattered across East Africa like beads on a string, these ancient ranges have been separated from each other for millions of years. Each mountain block acts like a sky island, cut off from its neighbours by lowland savannas and dry plains. Over time, plants and animals in these high-altitude refuges have diverged, evolving into unique forms. The Usambara Mountains, for instance, host chameleons and frogs that exist nowhere else on Earth. Their isolation has made them living museums of biodiversity, where each valley shelters a slightly different story. Cloud forests perched partway up many tropical mountains are among the most enchanting of these zones. Constant mist nourishes an abundance of epiphytes, plants that grow not in soil but upon other plants. Orchids dangle from branches, ferns sprout from mossy trunks, and bromeliads gather pools of water that become tiny aquatic worlds for insects and amphibians. The atmosphere here feels hushed, as though sound itself has softened in the fog. For a species, it is a delicate environment. Many rely on this near-constant moisture and cannot survive if cloud cover shifts due to warming climates or deforestation. Above the cloud forests, life becomes sparse yet equally fascinating. Alpine specialists are masters of endurance. Cushion plants in the Andes form dense mats to resist the cold. In East Africa's high peaks, giant lobelias and groundsels rise like surreal sculptures, storing water in their stems to buffer against freezing nights. Small mammals such as the viscacha, a rabbit-like creature, scurry among rocks, while predatory birds patrol the thin air. These ecosystems are fragile, existing at the very edge of what is possible, and yet they host organisms found nowhere else. Mountains also serve as barriers. Valleys and ridges can isolate populations just as effectively as oceans. Two populations of the same bird species might be separated by a peak too high to cross, leading each group to evolve along its own trajectory. Over time, such isolation gives rise to entirely new species. In this way, mountains are both creators and custodians of diversity, fostering novelty while holding it apart in pockets of endemism. The influence of mountains extends even further. By catching moisture and deflecting winds, they shape the climates of entire regions. The Himalaya, for example, helps sustain the South Asian monsoon by lifting moist air from the Indian Ocean and wringing it out as rain. The Rockies alter storm tracks across North America. These atmospheric effects ripple outward, influencing where forests grow, where grasslands stretch, and where deserts form. Even far from their slopes, mountains dictate life's possibilities. From a human perspective, mountains have always been places of awe, their sheer height suggesting closeness to the heavens. For other species, they are crucibles of adaptation. Each step upward feels like a migration across continents, compressed into a few hours of climbing. Life in these vertical landscapes demonstrates both incredible specialization and incredible fragility. When climates shift, Species adapted to narrow altitudinal bands can find themselves trapped with nowhere higher to go. And yet mountains remain timeless laboratories, endlessly experimenting with forms of life. Whether it is a frog that can survive only in a single misty valley, or a plant that has mastered the art of catching warmth in the coldest of nights, each tells a story written on the slopes. They are reminders that biodiversity is not spread evenly, but concentrated in the folds, ridges, and isolated summits of the world. Climb a mountain, and you move through climates stacked like the verses of a song. Each altitude hums with its own melody, sometimes lush and crowded, sometimes sparse and thin. Together they form a chorus that speaks to the creativity of life, guided by nothing more than the steady drop of temperature with height and the barriers of stone. Mountains in their silence sing. Mountains do more than rise above the land. They rearrange the sky itself. When moist air drifts across the landscape and encounters a wall of peaks, it has little choice but to climb. As it rises, the air cools, and cooler air cannot hold as much moisture. Clouds form, droplets gather, and before long rain falls on the windward slopes. This is orographic lift, the invisible push that wrings water from the sky. The result can be lush forests, dripping leaves, and rivers tumbling down green valleys. Yet the same mountains that create abundance on one side take it away on the other. By the time the air crosses the crest, it has shed most of its moisture. Descending air warms, humidity drops, and the leeward slopes are left parched. This is the rain shadow effect, a quiet architect of deserts. Nowhere is this contrast sharper than in the Himalaya and the Tibetan plateau. Moist air swept northward from the Indian Ocean slams into the southern face of the Himalaya, rising steeply over ridges that soar above 8,000 meters. The Indian subcontinent owes its monsoon rains largely to this dramatic uplift. Hillsides in Nepal and Bhutan gleam with rice paddies, jungles stretch along the foothills, and rhododendrons bloom in riotous colours each spring. Yet crest the range, and the story shifts entirely. On the northern side lies Tibet, a high, arid plateau sometimes called the roof of the world. Here, rainfall is sparse, vegetation thins to hardy grasses and shrubs, and wide expanses of rock and sand dominate. The same mountain chain that sustains the fertile plains of South Asia has, on its far side, built a near desert at altitude. Another striking example lies in South America, along the spine of the Andes. Moist air carried inland from the Pacific Ocean strikes the western slopes, but is swiftly depleted. Beyond the crest, the Atacama Desert stretches for nearly 1,000 kilometers, a place so dry that some weather stations have never recorded a single drop of rain. In parts of the Atacama, conditions are so extreme that they rival the surface of Mars. Specialized plants cling to life by harvesting dew or fog, while microorganisms survive within salty rocks, shielded from the relentless sun. This hyper-aridity owes its persistence not only to the Andes, but also to the cold Humboldt Current offshore, which chills the air and reduces its capacity to hold moisture. Geography conspires from multiple directions to enforce the desert's grip. Rain shadows can be found across the globe, sometimes subtle, sometimes dramatic. The Cascade Range in North America, for instance, divides the sodden forests of Washington's western slopes from the dry sagebrush plains to the east. New Zealand's southern Alps cloak their western flanks in temperate rainforest, yet cast long dry zones on the eastern plains of Canterbury. Each example repeats the same principle. Mountains make weather, and weather shapes ecosystems. For life, these sharp contrasts create opportunities as well as challenges. On the moist windward side, plants grow tall and dense, their leaves broad and soft, designed to capture light in a crowded canopy. Animals thrive in abundance. birds, insects and mammals supported by the sheer productivity of the land. Cross the ridge, and adaptations take on entirely different forms. Plants shrink, thicken, or arm themselves with spines. Leaves become waxy or hairy to conserve precious drops of water. Animals switch to nocturnal habits, emerging under cover of cool darkness to avoid the punishing heat of the day. Survival here is about efficiency, about squeezing existence out of the smallest gifts the land provides. The beauty of the rain shadow effect is its simplicity. It takes nothing more than air, water vapor, and mountains to craft two opposing worlds. The same atmospheric parcel that waters a forest can also, within a few hours of drifting downhill, parch a desert. It is as though the mountain acts as a cosmic switch, flipping from abundance to scarcity in a single ridgeline. And while the process itself is straightforward, the results ripple outward through culture and history. Fertile valleys on the wet sides of mountains have long drawn human settlement, farming and trade. The dry sides, though more difficult, often became routes of travel or places where hardy pastoralists carved out a living. In both cases, human choices were shaped by the same invisible hand that guided the plants and animals, the geography of rain and shadow. There is something poetic about a mountain shaping two completely different worlds with one gesture. Moisture condenses into life on one slope, while the other bakes in silence, its creatures ingenious in their resilience. It is a reminder that nature's contrasts often sit side by side, divided only by a ridge of stone. The rain shadow is not a harsh trick but part of the planet's design, a quiet balance of excess and scarcity. And in that balance, evolution has found endless room to work its craft. Rivers are not simply water in motion. They are lifelines, movers of sediment, shapers of valleys, and carriers of life itself. To follow the course of a river is to follow a story written in constant flux. For countless species, rivers act as both highways and fences, providing pathways for dispersal, while also keeping populations apart. In their floodplains and deltas, they nurture nurseries of abundance, yet in their rapids and channels, they carve boundaries that shape the destiny of entire lineages. The Amazon offers one of the most striking demonstrations of this dual role. Flowing for more than 6,000 kilometers, it gathers tributaries from across half of South America, weaving together the largest drainage basin on Earth. Its waters are not uniform. Some are white, churning with sediment eroded from the Andes. Others are black, steeped in tannins from decaying vegetation, dark as tea and acidic enough to dissolve nutrients differently. Where these rivers meet, life often responds with bursts of diversity. At the confluence of the Amazon and the Negro, the two waters run side by side for kilometers, refusing to mix at first because of their differences in temperature, speed, and chemistry. To fish and invertebrates, such boundaries are more than visual curiosities. They are ecological dividing lines. Populations adapt to one water type or the other, and over time, these preferences can foster new species. The Amazon's floodplain is another evolutionary stage. Each year, seasonal rains swell the river, inundating vast forests. Trees stand in water for months, fish feed on fallen fruits, and the landscape transforms into an aquatic labyrinth. These floods are both a challenge and an opportunity. Species that can synchronize with the rhythms of the flood pulse thrive. Fish lay eggs in submerged vegetation, birds nest in anticipation of the bounty, and amphibians time their breeding to pools that form and vanish. The constant rise and fall of water has created a system that rewards adaptability and specialization, ensuring that no 2 years are quite the same and that life must remain nimble. If the Amazon is a corridor that connects, the Congo River in Africa demonstrates how a river can divide and isolate. Cutting across the heart of the continent, The Congo is not only deep but also marked by rapids, waterfalls, and swift currents that serve as formidable barriers. For fish, these features create pockets of isolation. Populations trapped above or below rapids evolve independently, and the result is astonishing diversity. Cichlids, catfish, and other groups have radiated into forms adapted to microhabitats, rocky pools, fast-flowing channels, or calm backwaters. The river, far from being a uniform expanse of water, is a patchwork of evolutionary laboratories. The shifting of rivers over time also leaves an imprint. Meanders wander across floodplains, carving new channels, abandoning oxbow lakes and reworking habitats. These shifts fragment populations, bring together species that were once apart, and create mosaics of new opportunities. What appears to us as a slow change in a river's course is, for organisms tied to precise conditions, the difference between survival and displacement. Fish that specialize in certain flow speeds or sediment types can suddenly find themselves isolated when the river decides to bend a different way. Deltas add another layer to the story. At the mouths of great rivers like the Nile, the Mississippi, or the Ganges-Brahmaputra, sediments fan outward into wetlands and estuaries. These zones teem with productivity, serving as nurseries for fish, birds, and invertebrates. The mixing of fresh and salt water creates gradients of salinity, each niche occupied by species uniquely equipped to handle it. Juvenile fish often begin life in the protected shallows of a delta before venturing into the open sea, their survival tied directly to the sediments carried from far inland. In this sense, rivers not only connect continents, but also link entire realms of life, from mountain streams to the ocean. During times of climate upheaval, rivers have offered refuge. In the ice ages, when glaciers advanced and retreated, river valleys often remained habitable. Moisture collected along their courses, forests clung to their banks, and species retreated into these lifelines when surrounding regions grew inhospitable. Once climates warmed again, these refuges became launching pads for recolonization. The patterns of biodiversity seen today often trace back to the stability rivers provided when the wider world was unpredictable. For humans, rivers have long held similar power. They fed the earlier civilizations, carried traders and travellers, and provided fertile soil for agriculture. Yet for other species, rivers have been shaping destinies for far longer. They have dictated where lineages diverge, how adaptations are honed, and where life flourishes or fades. The quiet truth is that a river is never the same twice. Its flow shifts daily with rains, seasonally with floods, and geologically with the slow sculpting of land. Each of these scales interacts with evolution, bending the pathways of species in directions we often overlook. Rivers, then, are not just moving water. They are conveyors of genes, barriers that divide, and laboratories where novelty emerges. Their floodplains host nurseries of life, their deltas stitch together land and sea, and their shifting courses redraw the map of possibility. To watch a river flow is to watch evolution in motion, sometimes connecting, sometimes separating, but always guiding the restless creativity of life. Where the land meets the sea, the planet reveals some of its richest contrasts. The coastline is a restless boundary, neither wholly ocean nor entirely land, but something in between. Here, tides pull and push, waves break ceaselessly, and winds funnel nutrients from deep waters to the surface. This mixing zone is where life gathers in extravagant abundance. Coastal ecosystems may cover only a sliver of the earth, yet they account for an enormous share of its productivity. For countless creatures, this narrow fringe is the stage upon which survival, competition, and collaboration all play out. The secret behind much of this productivity lies in currents and upwelling. In certain places, steady winds push warm surface waters away from the coast. In response, colder water wells up from the depths to replace it, carrying with it a payload of nutrients that have been locked away far below the reach of sunlight. Suddenly, regions that might otherwise be barren bloom with phytoplankton, the microscopic plants of the sea. These tiny organisms multiply rapidly, forming the base of food webs that feed everything from anchovies to whales. The water turns into a living soup, dense with possibilities. The Benguela Current along the southwest coast of Africa is one of the finest examples of this process. Driven by persistent winds, it pulls nutrient-rich waters to the surface along Namibia and South Africa. The effect is dramatic. Fisheries thrive, seabirds gather in great colonies, and seals patrol the surf in search of prey. The productivity here rivals that of tropical rainforests, though the scene could not be more different. Rolling ocean swells meeting stark desert dunes, life bursting in a place that to human eyes looks empty and austere. The neighbouring Namib Desert tells a related story, one where the ocean's influence creeps inland not with rain but with fog. Along this coastline, cool currents chill the air, creating mists that roll ashore even when the skies above are bone dry. Plants and animals have adapted to harvest this ethereal resource. The famous Namib fog beetle, for instance, climbs to the crest of a dune each morning and angles its body so that droplets condense on its back and trickle down to its mouth. For a creature in one of the driest deserts on Earth, the fog is as good as rain. Here, the meeting of current and desert air produces one of the planet's most unusual partnerships, mist as lifeline. On the opposite side of the Atlantic, the Peru Current creates another spectacular upwelling system. Off the coast of South America, winds push surface waters away, drawing up nutrients that support immense schools of anchoveta. These small fish have long been the backbone of local fisheries, and their abundance in turn sustains guano birds, sea lions, and dolphins. At times, the productivity has been so overwhelming that it altered human history. Peruvian guano, rich in nitrogen, became a prized fertilizer in the 19th century, shipped across oceans to feed distant crops. All of this bounty traces back to the steady rhythm of currents and the generosity of the deep. Not all coastlines depend on upwelling. Some, like tropical coral reefs, flourish because of stability and clarity. Reefs thrive in nutrient-poor waters where competition forces efficiency. Corals, with the help of symbiotic algae, build sprawling underwater cities of calcium carbonate, and thousands of species find homes among their crevices. At higher latitudes, kelp forests dominate. Towering fronds of seaweed rise like underwater trees, swaying with the surge, providing shelter and food for fish, crustaceans and otters. Both systems, reefs and kelp forests, exist along coasts, yet their strategies differ. One is intricate and brightly coloured, a masterpiece of partnership between algae and coral. The other is swaying, flexible and shadowed, a haven of cool water abundance. The land-sea edge is also a crucible for adaptation. Creatures must endure shifting tides, waves, and salt spray. Crabs scuttle between rock pools, timing their forays with the retreat of the water. Mussels cling to stones with iron-strong threads, enduring both the pounding surf and the exposure of low tide. Shorebirds patrol the sand, probing for worms and shellfish, moving with clockwork precision to the rhythm of the tide. Few other habitats demand such versatility, and fewer still reward it with such concentrated resources. Yet coastlines are fragile. Shifts in wind or temperature can disrupt upwelling, starving entire food webs. In the Pacific, the El Niño phenomenon occasionally halts nutrient supply, and suddenly seabirds abandon nests. Fish numbers plummet, and marine mammals struggle. The bounty of the coast depends on balance, and even slight perturbations ripple through the system. Despite their vulnerability, coasts remain places of exuberance. A single square kilometre of estuarial reef can host more species than many entire landscapes inland. The interplay of currents, tides, and geology concentrates life into a thin ribbon that circles the continents. Standing at a shoreline, one might see little more than waves and sand, but beneath the surface the ocean is busily knitting together threads of productivity and diversity. What makes coasts so captivating is their duality, their edges, margins, boundaries, yet also connectors, linking the open ocean to rivers, linking continents to the sea. They embody contrast, deserts sustained by fog, seas bursting with life because of invisible winds, rocky pools harbouring creatures tough enough to withstand both drowning and drought twice a day. It is in these contradictions that coastal ecosystems shine, places where geography meets biology in concentrated form. At the edge of the land, with waves at your feet and the horizon stretching beyond sight, the richness of life owes itself to unseen currents and the deep generosity of the sea. This narrow strip, so small on a globe, carries more life than its size suggests, whispering of the power that comes when earth and ocean continually meet. There is something enchanting about islands. Cut off from the mainland, surrounded by water, they are like natural laboratories where life is given the tools of chance and time, then left to see what emerges. The rules here are different. Isolation shapes destinies, distances filter who arrives, and size dictates who can stay. For centuries, naturalists have looked to islands not just as remote outposts of life, but as windows into the mechanics of evolution itself. One of the most famous island stories belongs to the Galapagos. When Charles Darwin visited in the early 19th century, he noticed subtle but telling differences among the finches on different islands. Some had thick, powerful beaks for cracking seeds. Others had slender, delicate bills suited to probing for insects. The birds had descended from a common ancestor, but isolation on separate islands had set them on different evolutionary paths. Over time, their beaks became the tools of survival, tailored to each ecological niche. This process, adaptive radiation, unfolds when a few pioneering colonists arrive in an empty landscape and then diversify into many forms, each taking advantage of a slightly different opportunity. New Caledonia in the Pacific offers a botanical equivalent. This ancient fragment of Gondwana has been isolated for tens of millions of years. Its flora reads like a catalogue of evolutionary experiments. One of its most extraordinary plants, the kauri pine, towers above the forest, while nickel-loving species cling to metal-rich soils where few others can survive. The island's long separation has allowed lineages to persist that vanished elsewhere, making it both a refuge of ancient forms and a cradle of novelty. To wander its forests is to glimpse a world that feels half familiar, half forgotten, as if time itself took a detour there. Madagascar tells yet another tale, one where distance and time combine to create an entire world of endemism. Split from the African mainland around 160 million years ago, it has drifted in solitude ever since. The result is a landscape where more than 90% of plant and animal species are found nowhere else. Lemurs, with their wide eyes and varied calls, fill ecological roles that monkeys and apes occupy elsewhere. Chameleons flourish in dazzling diversity, their colours shifting with mood and environment. Even the baobab trees look as though they were sketched in a dream, their swollen trunks storing water against the dry season. Madagascar is a continent in miniature, a vast island where isolation has created an explosion of unique life. The principles behind island evolution can be traced through three main factors: distance, size, and the balance between immigration and extinction. distance acts as a filter. The further an island lies from a mainland, the fewer species can reach it. Birds may arrive on strong winds, seeds may float across seas, and in rare cases small animals may cling to rafts of vegetation. Once established, these pioneers face little competition and often diversify. Size determines how much life the island can support. Larger islands can sustain bigger populations and more habitats, reducing the risk of extinction and allowing more species to coexist. Smaller islands, by contrast, may host only a handful of species, each vulnerable to the slightest disturbance. This balance, species arriving and others vanishing, creates a kind of equilibrium. In the 1960s, ecologists Robert MacArthur and E.O. Wilson formalised the idea into the theory of island biogeography. Their work showed that the number of species on an island is not static, but the result of a dynamic interplay between colonisation and extinction. It was a revelation. Islands are not simply isolated collections of organisms, but stages where the drama of ecology is constantly unfolding. Isolation also produces some of evolution's most curious outcomes. On islands, size often takes surprising turns. Large animals sometimes become dwarves, shrinking to survive in limited environments. The extinct pygmy elephants of Mediterranean islands are classic examples. On the other hand, small creatures may swell into giants. The Komodo dragon, the world's largest lizard, is thought to have grown large in part because of island dynamics. Without competition from bigger carnivores, it filled the role itself. This phenomenon of dwarfism and gigantism is a signature of insular evolution, a reminder that constraints often fuel creativity. Beyond animals, plants too follow their own island rules. With fewer pollinators available, some plants evolve flowers that are less showy, conserving resources. Others, freed from mainland herbivores, lose their chemical defences or thorny armour. Traits honed for crowded, competitive continents can soften in isolation. Yet vulnerability often follows. When new arrivals, whether goats, rats or humans, step ashore, they can disrupt balances that held steady for millennia. Despite this fragility, islands remain crucibles of diversity. They illustrate how life responds when thrown into isolation with limited tools. Given enough time, small beginnings can blossom into entire communities unlike anything else on Earth. Islands are proof that even on the smallest patches of land, nature's inventiveness knows no bounds. To stand on an island is to feel both its limits and its possibilities. The sea marks a firm boundary, but within that frame, life has written some of its most imaginative chapters. From the beaks of Galapagos finches to the lemurs of Madagascar and the nickel-tolerant plants of New Caledonia, islands show what happens when geography sets the rules and biology plays along. They are reminders that separation need not mean silence. Often, it means symphonies, evolutionary experiments unfolding in harmony with isolation, distance, and time. If you were to sail through the islands of Southeast Asia, hopping from Borneo to Sulawesi, you might expect the forests, birds, and mammals to blend together seamlessly. After all, the distance between the two is not great, and from a boat the shorelines can appear almost interchangeable. Yet look more closely, and you find an invisible frontier, an ecological boundary as sharp as a drawn line on a map. On one side, tigers, orangutans and woodpeckers. On the other, cockatoos, marsupial cuscuses, and hornbills absent where you might expect them. This mysterious division is known as the Wallace line, and it has puzzled and inspired naturalists since the 19th century. The line is named after Alfred Russel Wallace, a contemporary of Darwin, who travelled extensively through the Malay archipelago. He noticed something peculiar. Islands to the west of a narrow strait were filled with Asian fauna, while those just to the east looked more like Australia in miniature. The difference was not subtle. Even though some islands were separated by only a few dozen kilometres of water, their wildlife followed entirely different evolutionary scripts. Wallace's keen observations gave us one of the earliest recognitions that geography itself sets hard boundaries on the spread of life. The explanation lies beneath the sea. During the Ice Ages, global sea levels dropped by more than 100 metres as glaciers locked away water. Vast areas of the Sunda Shelf, which now lie submerged, became exposed, connecting many of the western islands to mainland Asia. Elephants, tigers, rhinos and primates could roam freely across the joined landmass. To the east, however, the deep water channels of the Makassar Strait and the Lombok Strait remained barriers. Even when seas were at their lowest, these trenches stayed flooded, effectively isolating the islands of Wallacea, places like Sulawesi, Lombok and Flores. Animals adapted to the Australian realm could reach these islands, but those from the west could not cross. The result was a boundary that persisted for millions of years, enforced not by distance alone but by depth. Sulawesi, with its curious shape of twisting peninsulas, stands as a living testament to this separation. Its forests harbour marsupial cuscuses, babirusas with their extraordinary curling tusks, and hornbills with vivid casques. None of these are found just across the strait in Borneo. Conversely, Borneo is home to orangutans, proboscis monkeys, and leopards, creatures entirely absent from Sulawesi. A few species manage to straddle the line through flight or sheer luck, but the vast majority remain divided, as though obeying an unseen border patrol set by geology. The Wallace line also helps explain why Australia is so dominated by marsupials and monotremes, while Asia teems with placental mammals. The deep seas between them acted as barriers even during the lowest sea levels, limiting interchange. Birds, bats, and occasional reptiles were able to cross, but large mammals remained largely confined to their realms. Over millions of years, these restrictions reinforced distinct evolutionary trajectories. In Australia, kangaroos, koalas, and echidnas diversified with little interference. In Asia, elephants, primates, and cats did the same. The line became less a single border and more a broad transitional zone, a shifting frontier that still shapes patterns of biodiversity today. This interplay of barriers and dispersal highlights two key concepts in biogeography: vicariance and colonization. Vicariance occurs when populations are split apart by physical barriers, rising seas, mountain ranges, or shifting tectonics. Colonization happens when a few pioneers manage to cross a barrier, often by accident, and establish new populations. The Wallace line illustrates both forces. For most species, the deep channels enforced vicariance, keeping populations separated. For a daring few, like fruit bats or seafaring birds, colonization allowed them to leap across, blending elements of the two realms. The Wallace line is not the only such boundary on Earth, but it is one of the most famous because of its clarity. Stand in the forest of Borneo, and you walk in the company of gibbons, deer, and sun bears. Step ashore in Sulawesi, and you enter a different ecological stage entirely. It is as if the Earth itself decided to draw a curtain, letting one set of characters play on one side and an entirely different cast on the other. What is most striking is that the line is invisible. There are no fences, no dramatic changes in the terrain, only water between islands. Yet the distinction in species is undeniable. It reminds us that life does not spread evenly across the planet, but follows paths set by chance, history, and the hidden contours of the Earth's surface. The Wallace line endures as a living lesson in the power of geography, how a few dozen kilometres of sea, underpinned by deep trenches, can hold sway over millions of years of evolution. To trace its arc across the map is to see more than just a boundary. It is to glimpse the way barriers shape possibilities, how isolation fosters novelty, and how invisible lines can define entire realms of life. The Wallace line whispers that geography is never just background, it is the stage manager, deciding who enters and who stays behind. Deserts might appear empty at first glance, vast expanses of sand, stone or scrub shimmering in relentless sun, yet behind that apparent barrenness lies a world of invention, where life has mastered the art of making do with almost nothing. These drylands, which cover nearly 1/3 of the Earth's surface, are laboratories of endurance. Here, the limiting currency is not space or nutrients but water, and every plant and animal is a specialist in saving, seeking, or stealing it. The Sahara is the world's largest hot desert, stretching across North Africa in a sweep of dunes, gravel plains, and rocky plateaus. Rain can vanish for years, and yet even in this harshness, life persists. Acacia trees push roots deep into the soil, tapping hidden aquifers. Addax antelopes can go without free water for long stretches, drawing moisture from the plants they consume. Even humans have learned to survive here, moving with the rhythms of oases and trade winds. The Sahara demonstrates that deserts are not devoid of life, but are instead home to strategies so finely tuned they verge on the improbable. On the other side of the Atlantic lies the Sonoran Desert of North America, a place of extremes but also of surprising variety. Unlike the Sahara's monotone sands, the Sonoran blooms with diversity. Towering saguaro cacti lift their arms to the sky, storing water in accordion-like pleats that expand after rainfall. Many of its plants rely on crassulation acid metabolism, or CAM photosynthesis, a process that allows them to open their stomata at night to reduce water loss while still capturing the carbon dioxide needed for growth. The result is a botanical sleight of hand, plants that photosynthesize with minimal evaporation, thriving where water is more precious than gold. Animals here are equally resourceful. Kangaroo rats, for instance, never need to drink liquid water at all. They obtain every drop they require from seeds, metabolizing carbohydrates into both energy and water. Their kidneys are so efficient that their urine is thicker than syrup, conserving every possible molecule. Many creatures retreat from the day's furnace into burrows and emerge only after dusk. Nocturnality is not just a preference here, but a survival tactic. Under starlight, desert life stirs, owls glide silently, snakes hunt in cool sand, and pollinating bats sip nectar from night-blooming flowers. The desert may rest in daylight, but under moonlight it hums with activity. Australia's interior adds another flavour to the desert palette. Its arid lands are punctuated by bursts of colour after rare rains. Seeds that have lain dormant for years spring to life, carpeting the ground in ephemeral blooms of daisies and everlastings. This boom and bust rhythm is a hallmark of deserts worldwide. When water arrives, ecosystems explode with productivity. Plants flower, insects emerge, and animals breed in synchrony, taking advantage of the brief window. Then, just as quickly, the landscape quiets, returning to apparent stillness until the next pulse. Such pulses demonstrate that deserts are not barren but rather places of timing and restraint. Survival depends on recognizing when to wait and when to act. Ephemeral plants complete their life cycle in a matter of weeks, setting seeds before the soil dries again. Migratory birds time their journeys to coincide with sudden insect surges. Even large mammals, such as camels, embody this rhythm, storing fat reserves to endure long stretches between scarce rains. From a physiological perspective, desert plants are masterpieces of engineering. Succulents store water in thickened stems and leaves, often protected by spines that deter grazers and shade the plant's surface. Others, like creosote bushes, spread wide, shallow root systems to capture every fleeting shower. Some, astonishingly, can photosynthesize at extremely high temperatures without wilting, their cellular machinery built to withstand what would kill most plants elsewhere. Deserts also highlight the role of temperature extremes. Without clouds to hold in heat, days blaze and nights chill. It is common for temperatures to swing by more than 30 degrees Celsius in a single cycle of day and night. Life here must handle both fire and frost within 24 hours. Reptiles bask to raise body temperature in the morning, but seek shade by afternoon. Mammals grow thick coats to survive frigid desert nights, even as they endure scorching days. Flexibility is not an option, it is the essence of desert living. Despite their severity, deserts harbour cultural and ecological richness. Nomadic peoples have long navigated their shifting dunes, relying on knowledge passed down through generations to locate waterholes and track animal movements. Desert plants have provided medicines, food and shelter for thousands of years. And for modern science, deserts are proving grounds for astrobiology. If microbes can endure the Atacama or the Namib, perhaps life could persist on Mars. What might seem monotonous from afar is, up close, a patchwork of adaptations. Each cactus spine, each beetle's dew-harvesting shell, each seed waiting patiently beneath the sand speaks to the quiet brilliance of evolution. Deserts remind us that abundance is not the only measure of richness. Sometimes the true wonder lies in the ability to survive with almost nothing at all. So, far from being wastelands, deserts are landscapes of ingenuity. They are places where scarcity sharpens creativity, where extremes become the rule, and where life finds a way not by growing lavish but by growing clever. In their silence and sparseness, they reveal one of the deepest truths of biology, that resilience often shines brightest in the harshest of places. Across much of the world, the seasons change with a gentle turn. Spring slips into summer, summer fades to autumn, and winter lingers before the cycle renews. But in some regions, the year does not tiptoe between seasons at all. Instead, it swings like a pendulum, shifting dramatically between wet and dry. This is the realm of the monsoon, where vast winds switch direction and transform the landscape, bringing rhythms of abundance and scarcity that govern every living thing. The monsoon is born from the contrast between land and sea. Water warms and cools slowly, while land heats and chills much faster. During summer, the Asian continent grows hot under the unrelenting sun. Air above the land rises, drawing in moist air from the surrounding ocean. When this oceanic air is forced upward over the subcontinent, it condenses into towering clouds and unleashes torrents of rain. In winter, the process reverses. The land cools rapidly, winds blow outward, and dry conditions prevail. The result is one of the most dramatic seasonal reversals on the planet. A wind system so powerful it dictates not just weather, but the fates of forests, rivers, farms, and civilizations. South Asia demonstrates the drama of this cycle in full. The summer monsoon sweeps in from the Indian Ocean, delivering rains that sustain lush forests and agricultural fields alike. Entire landscapes are reborn after the first downpours. Parched soil softens, rice paddies flood, and rivers swell to life. Forests respond with an explosion of greenery, canopies dripping with moisture and buzzing with activity. Birds call more frequently, insects multiply in clouds, and mammals emerge to feed on the sudden flush of vegetation. Life here is tuned to the monsoon like an orchestra to its conductor, breeding, blooming, and migrating on cue. But the monsoon is not simply generous. It is also unpredictable, and its variations can mean the difference between feast and famine. Too much rain, and rivers burst their banks, inundating villages and washing away fields. Too little, and crops wither before harvest. This duality has etched itself into culture and tradition. Festivals, songs and rituals across South Asia celebrate the first rains, but they are always tinged with respect for the power of a system that can give so much yet take just as quickly. Further east, in Southeast Asia, the Mekong River embodies the seasonal drama in liquid form. Fed by monsoon rains, the Mekong swells until it reverses the flow of its tributary, the Ton Sap River, in Cambodia. Water surges into the Ton Sap Lake, expanding it more than fourfold during the rainy season. This flood pulse transforms the lake into one of the world's richest freshwater fisheries. Fish migrate in staggering numbers, feeding on nutrients brought by the waters, while birds flock to breed in the season of abundance. When the dry months return and the lake shrinks, the cycle begins anew. A heartbeat of water that sustains millions of people and countless species. Boom and bust cycles like this shape behaviours in striking ways. Many amphibians, for instance, time their reproduction with the rains. In India, frogs and toads emerge en masse after the first monsoon storms, filling the night with their calls as they rush to breed in newly formed pools. Insects seize the opportunity too, and the air becomes thick with swarms. Migratory birds travel thousands of kilometres to take advantage of this bounty, their journeys synchronised with rains that arrive almost like clockwork. For them, the monsoon is not simply weather, it is a reliable calendar written into their very biology. Plants also play to the rhythm. Teak trees, common in monsoon forests, shed their leaves in the dry season to conserve water, standing bare against the sky until rains return. With the first downpours, they leaf out almost overnight, transforming the landscape from sparse to dense in a matter of weeks. Grasses in savannas and open plains respond just as quickly, carpeting the land in green before fading back to gold as the dry season settles in. This quick-turn strategy ensures survival in a climate where predictability comes not from constancy, but from oscillation. The adaptability of life to these swings reveals the importance of timing. In monsoon regions, to miss time reproduction, migration, or growth can mean failure. Species that anticipate the rains too early risk exhausting resources, while those that wait too long may miss the brief window of plenty. Evolution has honed remarkable sensitivity to environmental cues. Changes in day length, shifts in humidity, and even the smell of petrichor, the scent of rain on dry earth, can trigger behaviour. What makes the monsoon truly captivating is its scale. This is not a local storm but a planetary system, tied to the tilt of the earth and the shape of continents. Winds from oceans, heat from land, and the pull of geography all converge to orchestrate seasonal abundance. And because of its vast reach, the monsoon has also shaped human societies in profound ways. Agricultural cycles, settlement patterns, and trade routes have all hinged on its arrival. Even today, modern economies still pulse with its timing, a reminder that civilization remains tethered to the sky's great breath. For all its might, the monsoon also holds a subtle beauty. The first rains after months of dryness have a scent and a sound like no other. Dust turns to mud, leaves shine, and rivers begin to sing again. It is a reminder that cycles of scarcity and abundance are not just trials but sources of renewal. In the landscapes governed by monsoons, life is not steady but pulsating, not static but endlessly responsive to the swing of seasonal winds. The rhythm of plenty set by air and water teaches a simple lesson. Stability is not always necessary for flourishing. Sometimes it is the very alternation between feast and famine, dryness and deluge, that creates the diversity and resilience of life. In the far reaches of the planet, where winters dominate and summers feel like fleeting guests, lie the cold realms. These landscapes are vast, stark, and at first glance forbidding. Yet within their frozen soils and abbreviated growing seasons, life has carved out remarkable strategies for survival. Here, Every drop of warmth is precious, every day of sunlight a chance to grow or migrate or reproduce before the curtain of cold falls once again. Stretching in a nearly unbroken band across North America, Scandinavia and Siberia is the taiga, or boreal forest. It is the largest biome on Earth, a green belt girdling the high latitudes, composed mostly of conifers, spruce, pine, fir and larch. These trees are designed for efficiency in a climate where time is short. Their needles, tough and waxy, resist desiccation and remain year-round, ready to photosynthesize as soon as light returns. Their conical shapes allow snow to slide from their branches, preventing damage in the heavy storms of winter. While species richness is lower than in warmer regions, sheer scale compensates. Billions of trees stand shoulder to shoulder, forming one of the greatest carbon stores on the planet. Animals in the taiga follow equally pragmatic rules. Moose browse on willows and aquatic plants during the brief thaw, building reserves for the cold months. Lynx prowl silently, their broad paws spreading weight across snow as they stalk snowshoe hares, which themselves cycle through populations in great booms and busts. Birds migrate in and out with the seasons. Warblers and thrushes arrive in summer to nest in the insect-rich canopy, then retreat south before the freeze. Those that remain, like chickadees and crossbills, endure the long nights by caching seeds or prying open cones. Every action here is dictated by the clock of a short summer and a long winter. North of the forest, where trees can no longer gain a foothold, lies the tundra. This biome is a mosaic of mosses, sedges, lichens and dwarf shrubs. The ground is underlain by permafrost, a layer of soil that remains frozen year-round. Only the surface thaws in summer, creating soggy, waterlogged conditions. Plants grow low to the ground, hugging the earth to avoid the scouring winds. Lichens, partnerships between fungi and algae, dominate the rocky patches, capable of photosynthesizing even in the dimmest light. In summer, the tundra bursts into colour as wildflowers bloom in quick succession, painting the landscape in purples, yellows and whites. It is a carnival of speed, for the window is short, barely a few months of growth before the cold sets in again. The tundra is also a realm of migrations. Caribou, or reindeer, move in vast herds, travelling hundreds of kilometres between wintering grounds in the taiga and summer calving areas on the tundra. These migrations are some of the largest in the animal kingdom, with tens of thousands of animals flowing across the open landscape like rivers of hooves. Birds too depend on the tundra's brief productivity. Millions of geese, sandpipers and plovers fly north each spring to take advantage of the insect explosion that occurs when the ground thaws. They breed, raise their young, and then depart south again before the snow returns. For these species, the tundra is not a permanent home but a seasonal nursery, one that must be used quickly and efficiently. Life at the edges of ice is even more constrained. Along the Arctic coastlines, polar bears patrol the sea ice in search of seals, waiting at breathing holes or ambushing prey resting on the floes. Seals themselves rely on the stability of ice for breeding dens, and walruses haul out onto it between dives for clams. When ice retreats too far, all these patterns are disrupted. The edge of the ice is a shifting, unpredictable frontier, yet it remains central to the survival of species that have no equivalent elsewhere. Nutrient bottlenecks are common in these cold regions. In the taiga, decomposition is slow, as low temperatures and acidic soils hinder microbial activity. Organic material accumulates as thick layers of peat and litter, locking away nutrients. Plants must therefore grow slowly and conserve what little they can recycle. In the tundra, water may be abundant on the surface in summer, but permafrost prevents deep rooting and nutrient availability is poor. Adaptations here are not about speed but thrift. Long-lived leaves, slow growth, and symbioses that help plants eke out an existence on what little the soil offers. Humans have always viewed these regions with a mix of awe and caution. Indigenous peoples such as the Sami in Scandinavia and the Nenets in Siberia developed lifeways closely tied to reindeer, following their migrations and adapting to the harsh rhythms of the land. Inuit communities along the Arctic coasts have long relied on seals, whales, and fish, reading the landscape in ways that reveal a deep attunement to a place most outsiders see as hostile. Their knowledge demonstrates that even in the most extreme settings, life, human or otherwise, can flourish when it adapts rather than resists. There is also a profound beauty in the seasonal extremes. In winter, the boreal forest is hushed under snow, its trees etched against pale skies. The tundra lies silent, frozen, and seemingly lifeless. But when summer arrives, light floods the land almost without pause. The sun circles the horizon, dipping but never disappearing, and plants and animals respond in a frenzy of activity. It is a race against time, a seasonal burst of productivity unmatched anywhere else. What takes a year in other ecosystems must be crammed into weeks here, and the urgency gives the landscape an electric intensity. Cold realms are not merely empty expanses of ice and trees. They are stages of resilience, proving that life can persist even when the odds appear stacked against it. They remind us that diversity does not always mean richness in species numbers. It can also mean richness in strategies. From lichens that photosynthesize at near-freezing temperatures to migratory birds that time their journeys with unerring precision, the inhabitants of these regions show ingenuity at every turn. In their stillness, the taiga and tundra speak of patience, endurance, and cycles measured in centuries rather than seasons. They may seem unforgiving, but they are also vital, storing carbon, reflecting sunlight, and regulating the Earth's climate. These cold realms may be distant, but they touch all lives, reminders that even in the most silent corners of the world, the story of life continues with quiet determination. Fire is often seen as a destroyer, a force that reduces forest to ash and grasslands to smouldering stubble. Yet in many ecosystems, fire is not a catastrophe, but a sculptor, shaping landscapes in ways that sustain diversity. Flames clear the ground, recycle nutrients, and open space for new growth. For plants and animals that have evolved alongside it, fire is not an intruder but an expected guest, part of the rhythm of life itself. The spark can come from many places. Lightning strikes are the most ancient source, igniting dry vegetation during thunderstorms. Volcanic eruptions, though rarer, also set landscapes alight. In recent millennia, humans have joined the mix, using fire deliberately to clear land, encourage game, or manage resources. While a blaze may look the same regardless of its origin, its ecological effects depend on timing, frequency, and intensity. These patterns, known as fire regimes, dictate whether a fire renews a system, devastates it, or transforms it into something entirely different. Australia is a continent where fire has long been a central player. Eucalypt forests, which cover vast areas, are exquisitely adapted to burn. Many species possess leaves rich in volatile oils that make them almost eager to ignite, ensuring that fire sweeps through with regularity. At first, this seems like botanical madness. Why make yourself flammable? But the strategy pays off. Fire removes competitors, recycles nutrients into the soil, and creates the open conditions eucalypts prefer. Their seeds, stored in woody capsules, often require the heat of flames to crack open, releasing a fresh generation onto the newly cleared ground. Some species resprout from protected buds beneath thick bark, emerging green even before the smoke has cleared. To walk in a burned Australian forest is to see blackened trunks sprouting vivid green shoots, a striking reminder of resilience written in flame. South Africa's fynbos, a shrubland rich in biodiversity, tells a similar story. This landscape is home to thousands of plant species, many of them found nowhere else. Fire is not an occasional visitor here, but an architect. Some shrubs produce seeds that lie dormant in the soil until fire cues their germination. Others release seeds only when flames consume the parent plant, a strategy known as serotiny. Proteas, with their striking blooms, often rely on this mechanism. Without fire, the dense thickets would eventually choke themselves, and diversity would dwindle. With fire, waves of regeneration sweep across the hillsides, keeping the community in dynamic balance. Fire works on the principle of patch dynamics. Not all areas burn at once, and not all fires are equally intense. Some patches may be scorched bare, others only lightly singed. This mosaic of burned and unburned areas creates a diversity of habitats. Animals recolonize from unburned refuges, plants sprout at different rates, and the landscape becomes a patchwork quilt of successional stages. For many species, this variability is crucial. Certain butterflies, for example, depend on early successional plants that flourish only in recently burned areas, while larger mammals may prefer the shelter of older regrowth. The constant interplay of flame and recovery sustains variety across scales. Even animals have developed relationships with fire. In Australia, black kites and other raptors have been observed carrying burning sticks in their talons, dropping them into dry grass to flush out prey. Whether or not this behaviour is widespread, it highlights the intimate ties between creatures and the flames that shape their world. In North America, woodpeckers known as black-backed woodpeckers specialise in recently burned forests, drilling into charred bark to feed on beetle larvae that invade dying trees. Fire opens niches not just for plants, but for entire communities of animals. Of course, not all fires are equal. Too frequent and species cannot recover. Too rare and fire-adapted systems lose their diversity. Balance is key. For thousands of years, indigenous peoples in Australia, North America and elsewhere practiced fire stick farming and controlled burning, creating mosaics that promoted both biodiversity and human livelihoods. These practices show that humans are not merely victims of fire, but participants in its ecological role. In contrast, modern fire suppression in some regions has allowed fuels to build up, leading to megafires of unprecedented intensity. Where flames once renewed, they can now overwhelm, reminding us that harmony with fire depends on understanding its patterns rather than fighting them outright. The paradox of fire is that destruction and creation come hand in hand. After flames sweep through, the soil is enriched with ash, sunlight reaches the ground unhindered, and nutrients locked in old biomass are suddenly available. Grasses sprout quickly, wildflowers bloom in profusion, and shrubs and trees begin the slow climb back. In these moments, diversity often peaks, as pioneers thrive in the open conditions and wildlife flocks to the bounty of new growth. A burned landscape is not an end but a beginning, an interval of fertility disguised as devastation. In colder realms, fire is rare, but in drylands and Mediterranean climates, it is fundamental. Pine forests in North America have cones sealed with resin that only fire can melt, releasing seeds. Grasslands across the world use fire as a reset button, preventing trees from dominating and maintaining open plains. The story repeats with variations across continents. Fire, far from being a universal villain, is a keystone process, sculpting systems as surely as rainfall or soil. To understand fire as a landscape designer is to appreciate its dual nature. It is dangerous, certainly, capable of wiping out towns or ecosystems if conditions align. But it is also generous, renewing soils, fostering diversity, and keeping ecosystems dynamic. Fire is a reminder that nature does not always follow human notions of safety or permanence. It works instead with cycles of disturbance and recovery, weaving resilience through apparent chaos. When you see a charred hillside, it is tempting to think only of loss, yet look closer, and you may notice green shoots emerging from blackened stems, flowers pushing through the ash, and birds returning to perch on scorched branches. Fire speaks in a language of renewal, one that life has been fluent in for millions of years. The flames may consume, but the story they leave behind is one of rebirth, diversity, and landscapes forever shaped by fire's touch. Water has a quiet patience. Give it time, and even the hardest stone will yield. Nowhere is this more visible than in landscapes of limestone, where rain laced with carbon dioxide seeps into cracks and crevices, slowly dissolving the rock. Over thousands and millions of years, entire subterranean worlds are carved out. Caves, sinkholes, underground rivers, and aquifers that run like hidden veins beneath the surface. These karst landscapes, named after a region in Slovenia where such features were first studied, are proof of water's ability to sculpt not just the surface of the earth, but its secret interior. Above ground, karst often appears dramatic and otherworldly. In Southeast Asia, limestone towers known as karst pinnacles rise like blades from the forest, their sheer walls streaked with vegetation. These towers are the remnants of long dissolution, where softer rock has vanished and the hardest ridges remain. Their steep cliffs shelter unique plants and animals, often isolated by sheer rock faces that prevent easy movement. Endemism thrives in such isolation, with species of snails, orchids, and insects clinging to habitats that exist nowhere else. The surface is striking enough, but the real marvel lies beneath. Caves form when groundwater enlarges fractures, eventually connecting them into vast chambers and passageways. The Dinaric Alps of the Balkans hold some of the world's most intricate cave systems, a labyrinth of tunnels stretching for hundreds of kilometers. These caves are not silent voids, but ecosystems in their own right. They are powered by nutrients washed in from above, leaves, wood, and soil organisms carried by water into the dark. Once there, they become the foundation for entire food webs, supporting creatures uniquely adapted to the eternal night. In these lightless environments, evolution takes unusual paths. Eyes become unnecessary and often disappear altogether. Pigmentation fades until animals are ghostly pale. Senses of touch and smell sharpen, compensating for the absence of vision. The olm, a cave-dwelling salamander from the Dinaric karst, exemplifies this adaptation. It can live for decades in total darkness, feeding on tiny crustaceans and enduring months without food thanks to a remarkably slow metabolism. Blind fish, translucent shrimp, and specialized insects, collectively known as troglobites, are further examples of life that has abandoned light, yet flourished in its absence. Water running through karst also feeds aquifers, storing vast amounts of fresh water. Unlike the slow seepage in other rocks, water in karst moves quickly through channels and conduits, sometimes travelling long distances underground before emerging again at springs. These springs often form true oases. In otherwise dry regions, the emergence of clear, cold water from stone transforms the landscape. Plants gather thickly, animals come to drink, and humans have long built settlements nearby. The link between karst aquifers and surface life is profound. What happens underground ripples outward into fields, forests, and communities. The chemistry of karst adds another layer of intrigue. As dissolved limestone reprecipitates, It builds stalactites that drip from ceilings and stalagmites that rise from the floor, slowly growing toward each other until they form columns. These mineral sculptures are time capsules, recording changes in rainfall and climate as they grow. Scientists can analyze their layers much like tree rings, reconstructing histories of droughts, floods, and shifting monsoons that shaped human and ecological destinies above. In this way, caves are not only habitats but archives, their dripstones keeping memories far older than any living witness. Despite their apparent isolation, subterranean systems are tightly linked to the surface. Nutrient pathways connect forests above to caves below, and rivers emerging from karst springs often sustain far wider ecosystems downstream. In Southeast Asia, fish species migrate into flooded caves during monsoons, blurring the line between surface and underground. Bats, roosting in enormous cave colonies, deposit guano that fertilizes both subterranean and external environments. The exchanges are constant, showing that even hidden realms contribute to the wider fabric of life. Karst environments are also fragile. Because water flows so swiftly through their porous networks, pollutants can spread quickly and without filtration. A single contaminated sinkhole may poison springs kilometers away. Overuse of groundwater can dry aquifers, collapsing caves or leaving springs lifeless. The delicate organisms of the underground, already specialized to extreme conditions, are particularly vulnerable. Their survival depends on the continued health of the invisible rivers flowing through stone, and yet, despite their vulnerability, karst landscapes hold a kind of magic. They remind us that much of the world operates out of sight. While forests and savannas draw our eyes with their obvious life, caves whisper of hidden processes, of creatures that thrive without sunlight, of waters that travel silently beneath our feet. Standing at the mouth of a spring, or in the cool depths of a cavern, one can sense that these places are not inert voids but living systems, humming quietly in the dark. From towering limestone cliffs wrapped in misty jungle, to subterranean streams where blind fish drift in ghostly silence, karst shows the creativity of water and rock in partnership. What begins as a raindrop dissolving a grain of calcium carbonate can end as an entire ecosystem shaped by stone. These hidden worlds are part of the planet's intricate design, a reminder that life finds its way not only where the sun shines, but also in the shadows beneath. Beneath every forest, grassland and desert lies a hidden foundation, one that quietly dictates who can grow and who cannot. Soil, often dismissed as mere dirt, is in fact the silent stage manager of ecosystems. Its chemistry, born from the rock it weathers and the processes that shape it, decides which plants will flourish, which will struggle, and which will never even take root. From acidity to trace metals, from nutrient richness to stubborn poverty, the ground beneath our feet is as much a creator of biodiversity as climate or geography. Soils begin with parent rock, granite, basalt, limestone, sandstone. Each breaks down differently, releasing its own suite of minerals. Rainfall, temperature, and biology further sculpt these particles, mixing organic matter with broken stone to form the medium of life. Yet not all soils are generous. Some cradle plants with abundant nutrients, while others are stingy or downright toxic. It is in these challenging soils that nature often reveals its most remarkable adaptations. Serpentine soils provide one of the most striking examples. Formed from ultramafic rocks rich in magnesium and heavy metals, they are chemically extreme. Their calcium to magnesium ratios are inverted compared to most soils, often containing more nickel, chromium or cobalt than many plants can tolerate. For most vegetation, serpentine ground is a hostile place. Roots burn, nutrient balance collapses, and seedlings fail. But where most species falter, a select few thrive. These specialists, adapted to the chemical oddities, create islands of endemism known as serpentine barrens. In California, serpentine outcrops support a surprising array of endemic plants: jewel flowers, serpentine columbines, and dwarf manzanitas, all of which tolerate conditions that exclude their neighbours. To walk from ordinary soil onto serpentine is to witness a sharp ecological boundary. Lush oak woodland gives way suddenly to sparse, stunted vegetation dotted with unusual species. The effect is almost as dramatic as stepping from forest into desert, yet the cause is invisible chemistry underfoot. A similar story unfolds in the Balkans, where serpentine hills host distinctive plant communities that exist nowhere else in Europe. Lateritic soils tell a different tale. Common in the tropics, they are formed under intense weathering, where heavy rainfall leaches nutrients away. What remains is iron and aluminum-rich earth, often coloured a vivid red. At first glance, these soils seem exhausted, stripped of fertility by relentless leaching. Yet they sustain some of the richest ecosystems on the planet. Tropical trees grow vast root networks to capture and recycle nutrients quickly, pulling them from decaying litter before rains can wash them away. Mycorrhizal fungi form intimate partnerships with roots, extending their reach and helping plants tap phosphorus locked in the soil. In these regions, survival is not about tolerating toxins, but about speed and efficiency. Nutrients must be captured almost the instant they appear. Such extreme conditions, whether too harsh, too poor, or too fleeting, often give rise to edaphic endemism, species restricted to specific soil types. Because competition is less intense on these chemical outposts, plants that can endure the hardships gain safe havens. Over evolutionary time, this leads to specialization and eventually unique floras. These soil-driven micro-hotspots of diversity are easy to overlook. A barren hillside of scrubby vegetation might seem unremarkable, until one realizes that nearly every plant growing there is a local specialist, part of a community found nowhere else on Earth. The influence of soil chemistry ripples outward beyond plants. Insects, birds, and mammals depend on the plant community, so shifts in soil composition indirectly shape animal diversity as well. A butterfly that relies on a serpentine wildflower will be confined to serpentine barrens. Birds feeding on the seeds of lateritic forest trees are tied to the health of those nutrient-poor soils. Soil, though hidden, builds entire networks of dependence. Even within seemingly uniform landscapes, subtle differences in pH or trace minerals can create mosaics of vegetation. A patch of acidic ground may host heaths and blueberries, while a nearby alkaline patch grows grasses and herbs. To the casual observer, the landscape blends together, but for plants, these chemical micro-variations are as decisive as mountain ranges or rivers. The role of soils in shaping biodiversity also highlights an important truth. Richness does not always arise from abundance. Sometimes it comes from constraint. Harsh soils impose limits that drive evolution toward novelty. In California, many of the state's rare and endangered plants owe their existence to serpentine outcrops. In South America, nutrient-poor white sand forests of the Amazon harbour their own distinct species, adapted to scarcity in a sea of fertility. These examples show that difficulty can be as creative as ease when it comes to generating life's variety. Soils also hold memory. Layers of organic matter, clays, and minerals record the passage of time, storing information about past climates and vegetation. In stalwart laterites or fragile peat bogs, history is written grain by grain. To scientists, soils are not just substrates but archives, revealing how ecosystems once functioned and how they may respond in the future. For all their quiet influence, soils are often overlooked, treated as uniform backdrops rather than active players. Yet they whisper their preferences constantly. This plant may pass, that one may fail, this one alone may thrive. Chemistry chooses, and biology adapts. From toxic metals to leached clays, from acidic bogs to alkaline flats, the Earth's skin is a patchwork of challenges and invitations. Life, ever inventive, accepts both with equal enthusiasm. A red hillside in the tropics, a stony serpentine outcrop, a sandy river terrace, all become stages where evolution writes new lines. In the end, the lesson is simple but profound. Beneath every leaf and root lies the unseen hand of geology, quietly guiding who prospers and who disappears. The soil is not silent after all. It speaks in the language of chemistry, and the chorus of plants and animals above ground sings in response. Nature does not always draw crisp borders. More often, it prefers transitions, places where one ecosystem blends into another, where forest thins into savanna, or shorelines slip into the sea. These transitional zones, known as ecotones, are among the most fascinating features of the living world. They are places of overlap and tension, where species from two different communities meet and mingle, sometimes cooperating, sometimes competing. Edges are rarely quiet. They are busy, noisy, and full of possibility, and for that reason they are often richer in diversity than the habitats they separate. Consider the boundary between forest and savanna in Africa. Here, tall trees give way gradually to open grasslands, and the mixture supports both forest dwellers and grassland specialists. Monkeys leap between branches at the margin, while antelope graze nearby in the open. Elephants, ever the great ecosystem engineers, wander between the two, sometimes toppling trees and pushing the edge back, sometimes encouraging growth by dispersing seeds. The mosaic is dynamic, shifting over years and decades, depending on rainfall, fire, and grazing. For animals, this instability is not a hindrance but an opportunity. A patch of woodland offers shade and fruit, while the adjacent grassland provides grazing and clear sightlines against predators. Species that can exploit both environments find themselves at an advantage. The same principle appears in aquatic systems. Along tropical coasts, mangrove forests often fringe the land, their tangled roots anchoring muddy shores. Just offshore, seagrass meadows spread across shallow waters, their blades swaying with the tides. The zone where these two systems meet is a haven for biodiversity. Juvenile fish find refuge among mangrove roots before venturing into seagrass beds, using both habitats as stepping stones in their life cycles. Crabs scuttle between the two, feeding on detritus in one and sheltering in the other. Sea turtles too graze in seagrass while resting in the shelter of mangroves. The richness comes not from one habitat alone, but from their intersection, where food, shelter, and safety overlap. Edges boost diversity because they bring together two sets of species while adding specialists of their own. Ecologists call this the edge effect, the tendency for boundaries to hold more species than either adjacent system. A hedgerow in Europe may host woodland birds, field-dwelling mammals, and species that prefer the shrubs of the border itself. Wetlands along rivers can be crowded with both aquatic and terrestrial organisms, from frogs and dragonflies to deer and herons. These zones are not simply mixtures but hotbeds of interaction. Competition, predation, and cooperation all intensify, producing communities that are constantly in flux. Yet edges are not without risks. Too much edge can fragment ecosystems, exposing species to dangers they would not face in the core of their habitat. Forest interior birds, for example, may suffer when edges allow predators or invasive species to intrude. Small patches of woodland surrounded by farmland often experience higher nest predation because edges make them accessible to crows, cats, and other opportunists. Light and wind penetrate further into the forest, altering microclimates and making conditions less suitable for shade-loving plants. In this way, edges can be both boon and burden, their benefits depending on context and balance. Some ecotones are ancient and enduring, shaped over millennia. The Sahel, stretching across Africa south of the Sahara, is a band where desert shades into savanna. Its boundaries shift with rainfall, advancing in dry years and retreating when rains return. Species here are adapted to uncertainty, capable of thriving in either drier or wetter spells. Other ecotones are short-lived, forming after disturbances like fire, storms, or flooding. These temporary edges can be particularly rich, as pioneers and opportunists move in quickly before one ecosystem eventually reclaims the ground. Edges also act as tension zones where evolution plays its hand. Populations from two distinct environments may meet and interbreed, creating hybrid zones. Sometimes these hybrids are less fit, reinforcing separation. Other times they thrive, introducing new genetic combinations that expand possibilities. The blending of ranges in ecotones can therefore accelerate change, making boundaries places of both ecological and evolutionary creativity. For humans, edges have long been attractive. Agricultural fields often lie at forest margins, where soils are fertile and water is available. Villages and cities frequently grow along rivers, exploiting the interface of land and water. Our own history has been shaped by these transitional zones, where the resources of two ecosystems could be drawn upon at once. But as landscapes become increasingly fragmented, edges proliferate unnaturally, sometimes to the detriment of species that rely on core habitats. Managing this balance, keeping some edges while preserving intact expanses, is one of the great challenges of conservation. Despite the risks, the fascination of edges lies in their vibrancy. Walk along a forest margin at dawn, and you may hear twice as many bird calls as deep inside the woods. Stroll a salt marsh, where grasses give way to mud flats, and you will find fiddler crabs, wading birds, and fish mingling in one place. These intersections remind us that life is not confined to rigid categories. It spills over boundaries, tests limits, and thrives in the in-between. Edges and ecotones show that richness often lies at the seams. Forest meeting grassland, mangrove meeting sea, desert shading into savanna. Each of these is a conversation between ecosystems, a dialogue carried out in roots, wings, and hooves. Diversity swells where two worlds touch, even as risks accompany the benefits. They are places of exchange, creativity, and constant change, proving that nature's most interesting stories often happen not at the centre, but at the margins. The landscapes we see today are more than static scenery. They carry memories, etched not in words but in patterns of life. During the repeated pulses of the ice ages, when glaciers advanced and retreated like the tides of deep time, species were pushed, squeezed, and scattered. Some vanished altogether, but many found safe havens, refugeia, where conditions remained tolerable even in the harshest cold. When the ice finally melted, these refugees became launching pads for recolonization, sending waves of plants and animals northward to repopulate the continents. The echoes of those journeys remain visible in the richness and distribution of species today. The rhythm of the ice ages was relentless. Over the last 2.5 million years, massive glaciers expanded and contracted in cycles lasting tens of thousands of years. During cold phases, ice sheets smothered northern latitudes, stretching across much of North America and Europe. Temperate forests, unable to survive beneath the ice, retreated southward. Grasslands and tundra spread in their place. For organisms accustomed to milder conditions, survival depended on finding sheltered regions where climate, topography, and geography combined to provide respite. In Europe, 3 peninsulas, those of Iberia, Italy, and the Balkans, served as vital refugia. Their southern locations, buffered by mountains and seas, allowed species to persist while glaciers covered much of the continent. Oaks, chestnuts, and other broadleaf trees held on in valleys and lowlands, waiting out the cold. Animals like roe deer and wild boar also found sanctuary. When the ice sheets retreated, these populations expanded northward once more, repopulating lands that had been barren. Today, genetic studies confirm these histories. Variations in DNA among modern populations reveal which lineages survived in particular refugia and how they spread. Iberian oaks, for example, carry distinct genetic signatures from those that survived in the Balkans, a living record of separate safe havens during the ice. The Balkans, with their complex terrain and varied microclimates, stand out as especially important. Here, mountains created pockets of warmth and moisture where even delicate plants could persist. Endemism flourished in these shelters, and to this day the Balkans remain a hotspot of biodiversity in Europe. What appears as a simple concentration of unique species is in fact the legacy of repeated survival during glacial hardship. Every rare flower on a Balkan mountainside tells a story of persistence against advancing ice. Across the Atlantic, North America's story is similar, but shaped by different geography. As ice sheets spread south from Canada, temperate forests retreated into the southeastern United States. The Appalachian Mountains acted as a major refuge, their ridges and valleys providing shelter from the worst of the cold. Many species survived here, tucked into hollows and slopes that offered milder conditions. When the glaciers melted, the Appalachians became sources of recolonization, sending plants northward to repopulate much of the continent. The Appalachian region remains rich in endemic species, particularly salamanders and forest plants, a testament to its role as a long-term refuge. Refugia were not just places of static survival, but also of subtle change. Populations trapped in isolation often diverge genetically, accumulating differences over millennia. When they expanded again, those differences sometimes persisted, creating distinct lineages within a species. In this way, ice ages did not merely shuffle life around, but actively generated diversity. Genetics serves as the timekeeper, allowing modern scientists to trace back these separations and reunions. A butterfly species in northern Europe may carry markers showing its ancestors once hid in Iberia, while a tree in the Alps may reveal roots in the Balkans. The DNA is like a diary, recording migrations no human ever witnessed. These legacies explain why certain regions today overflow with endemics. The southern European peninsulas, the Caucasus, the southern Appalachians, all are zones where life once huddled in refuge. Their richness is not accidental, but earned through endurance. When climates stabilized, the survivors spread outward, but many also lingered, continuing to diversify in the refugia themselves. These areas are museums and cradles at once, holding ancient lineages while simultaneously generating new ones. The concept of refugia extends beyond ice ages. In arid times, rainforests contracted into smaller patches, leaving dry savannas in between. When wetter periods returned, forests expanded again from those green islands, stitching themselves back together. The Amazon today bears evidence of this pattern. Pockets of exceptional diversity align with suspected refuges from past dry spells. Just as glaciers pushed life into corners in the north, drought sculpted safe havens in the tropics. The principle is the same: landscapes remember. The persistence of refugia also highlights the importance of geography in shaping resilience. Mountains, with their range of altitudes, offer multiple microclimates in close proximity. Valleys and gorges concentrate warmth and moisture. Coastal regions benefit from oceanic moderation. These features allowed small areas to shelter disproportionate amounts of diversity. becoming sanctuaries when the wider world turned hostile. Without them, many species we take for granted today might not exist at all. What is striking is how the ancient movements of ice and climate still influence modern patterns. A forest in Scandinavia may look uniform, yet the genes of its trees trace back to distant refugeia. A salamander in the Appalachians may appear ordinary, yet it belongs to a lineage shaped by isolation during glacial advances. Even our agricultural staples such as oaks and chestnuts owe their current distributions to these repeated retreats and returns. The memory of the landscape is written not in stone alone, but in living organisms themselves. There is also a lesson in fragility. Refugeia were vital because they provided stability when the rest of the world shifted. Today, as climates change rapidly once more, such refuges remain critical. Cool ravines, shaded slopes, and isolated valleys may again serve as shelters for species unable to cope with shifting conditions. Conservation efforts increasingly focus on identifying and protecting modern refugia, recognizing their role as both time capsules and lifeboats. To see a grove of ancient oaks in Iberia or a wildflower meadow in the Balkans is to glimpse more than beauty. It is to see resilience embodied, the living memory of a time when ice sheets ground across the land and survival meant clinging to small corners of habitability. These places remind us that biodiversity is not simply about the present moment. It is a tapestry woven through cycles of expansion and retreat, survival and recolonization. Refugia and their legacies prove that landscapes hold memory, not just in rocks and soils, but in the living patterns of species themselves. The next time you see a region unusually rich in life, consider that its abundance may be the echo of ancient winters and forgotten shelters, the quiet persistence of life when the world grew cold. Where land and water meet in restless embrace, wetlands, floodplains, and deltas emerge as some of the most dynamic ecosystems on Earth. These landscapes are never fixed. They shift with floods, build and erode with sediments, and pulse with nutrients that sustain a remarkable abundance of life. Far from being stagnant swamps, they are engines of renewal, turning mud and water into productivity so vast that it feeds millions of creatures, including people. At the heart of these systems is movement. Rivers carry sediments downstream, tiny fragments of rock and soil eroded from faraway mountains. Along the journey, nutrients join the flow, swept into the current from fields, forests, and decomposing matter. When the river slows, whether by spilling onto a floodplain or fanning out into a delta, these particles settle. What might seem like simple mud is in fact a gift of fertility. Each flood deposits fresh layers, recharging soils, creating mosaics of channels, marshes, and backwaters. Life responds exuberantly to these periodic transformations. The Okavango Delta in Botswana is a prime example of renewal written in water. Fed not by local rain but by distant storms in the Angolan highlands, the Okavango River swells seasonally, spilling across the Kalahari sands. Instead of reaching the sea, its waters spread and sink into the desert, creating a shifting oasis of lagoons, floodplains, and islands. This annual flood arrives during the region's dry season, when animals need it most. Elephants, hippos, and antelope converge on the delta's channels, while birds gather in dazzling numbers to feed and breed. The productivity of the Okavango comes from its shifting character. No 2 years are alike, and life here thrives on the unpredictability of the flood. Further west, the Pantanal of South America holds the title of the world's largest tropical wetland. Spread across Brazil, Bolivia, and Paraguay, it floods seasonally with waters from the Paraguay River. These floods expand the Pantanal into a watery wonderland, a patchwork of open water, floating meadows, and gallery forests. The richness of wildlife here is astounding. Jaguars stalk along riverbanks, giant otters hunt fish in backwaters, and hyacinth macaws wheel overhead. During high water, fish migrate into flooded forests to feed on fruits and seeds, carrying nutrients back into the aquatic system. When waters recede, the floodplains shrink, concentrating fish and other prey in smaller pools, which in turn fuels predators. The boom and bust cycle, driven by the river's pulse, creates an ecosystem of perpetual abundance. The Mississippi Delta tells a more human-shaped story. For thousands of years, the river deposited sediments at its mouth, building a vast deltic plain that spread into the Gulf of Mexico. These sediments not only built land, but also nourished wetlands that supported extraordinary fisheries and bird populations. Migratory waterfowl, shrimp, and oysters all owed their productivity to the muddy generosity of the river. Yet modern attempts to tame the Mississippi with levees and dams have altered this balance. By trapping sediment upstream and preventing floods from spreading across the delta, humans have starved the system of renewal. Wetlands shrink, coastlines retreat, and storms bite harder at the land. The lesson is clear. Deltas survive only when rivers are allowed to shift and build, not when they are frozen in place. Wetlands and floodplains are not just rich in biodiversity, they also act as powerful carbon sinks. Their waterlogged soils slow the decomposition of organic matter, trapping carbon that would otherwise return to the atmosphere. Peatlands in particular store immense amounts of carbon over millennia. This service is invisible but crucial, helping regulate global climate. At the same time, wetlands buffer floods by soaking up excess water, filter pollutants from rivers, and recharge aquifers. They are, in short, guardians as well as providers. For birds, these ecosystems are indispensable. Migratory species depend on wetlands as refueling stops along their journeys. The Pantanal and the Mississippi flyways see millions of birds congregate in seasonal abundance, feeding on insects, fish, and aquatic plants before continuing their travels. Some species time their entire breeding cycles to the flooding of particular wetlands. The sight of flocks rising in synchronized flight is not just a spectacle, but a visible sign of the productivity generated by mud, water, and shifting channels. The fisheries sustained by floodplains and deltas are equally vital. Seasonal floods trigger breeding queues for countless fish species. In the Amazon basin, for example, floods carry fish into forests where they feed on fallen fruits, dispersing seeds in the process. In Asia, the Mekong's floodplains support one of the largest inland fisheries on Earth, providing protein for tens of millions of people. Such productivity is not the result of stability but of change, the regular rise and fall of water creating pulses of fertility. Despite their resilience, wetlands and deltas are among the most vulnerable landscapes. Dams disrupt natural flooding, starving ecosystems of sediment and nutrients. Agricultural drainage and urban development convert wetlands into fields and cities, erasing habitats that took millennia to form. Climate change adds another layer of threat, altering rainfall patterns, raising sea levels, and increasing the severity of droughts and storms. The very qualities that make these systems productive, their dependence on flux and movement, also make them sensitive to disruption. Yet restoration is possible. In parts of Europe, rivers have been reconnected to their floodplains, reviving wetlands that had been drained. In Louisiana, projects aim to divert parts of the Mississippi back into wetlands, allowing sediment to rebuild lost land. These efforts recognize that wetlands cannot be preserved as static parks. They must be allowed to move, to flood, to breathe in their natural rhythm. What makes wetlands, floodplains, and deltas so captivating is their paradox. They are both chaotic and reliable, destructive and life-giving. A flood can sweep away fields one season and deposit fertile silt the next. A wetland can appear stagnant but quietly filter water, sequester carbon, and shelter young fish. They are places of abundance born out of disturbance, engines of renewal disguised as muddy expanses. To stand in the Pantanal as the waters rise, or watch the Okavango spread across the desert, or see the Mississippi winding its muddy braids into the sea, is to witness life at its most exuberant. These landscapes remind us that fertility often comes from flux, that renewal requires movement, and that the meeting of water and land is one of the most powerful partnerships on Earth. Human beings do not merely live on the land. We carve it, pave it, and rearrange it into grids of fields, roads, and cities. From the air, the patterns are striking. Highways cutting straight lines through forests, farmland stitched into geometric mosaics, suburbs blooming like strange new ecosystems. To us, these are signs of order and progress. To wildlife, however, they are often barriers, breaking continuous habitats into fragments, and forcing animals to navigate a landscape that suddenly feels like an obstacle course. This is the essence of human geography's impact on biodiversity. We do not just share space with other species, we redesign the map they must live by. Roads are one of the most powerful of these human-made barriers. They seem harmless enough, ribbons of asphalt carrying vehicles from place to place, yet to a frog, a hedgehog, or even a large mammal like a bear, a road can be a perilous frontier. Traffic divides populations, prevents migration, and often results in collisions that claim the lives of countless animals each year. For creatures that rely on seasonal movements, say amphibians seeking breeding ponds or ungulates following forage, roads can be the difference between survival and decline. In some regions, wildlife mortality from roads rivals predation as a limiting factor. From the perspective of a badger, the highway system might feel less like convenience and more like an endless series of death traps. Fragmentation extends beyond roads. As forests are cleared for agriculture or urban expansion, continuous habitats become smaller patches, separated by fields, fences, or housing estates. These fragments often cannot support the same richness of species as the original, unbroken expanse. Edge effects creep in. Increased light, wind, and human disturbance make conditions less suitable for interior species. Birds that nest deep in forests, for instance, may find themselves exposed to predators and competitors at the boundaries of shrinking patches. What remains is often a collection of ecological islands, each too small to hold the full orchestra of species that once played there. Yet human landscapes are not only destructive, they can also be reimagined. Across Europe, for example, greenbelts have been established around cities to preserve open space and corridors of habitat. These green belts prevent urban sprawl from consuming every surrounding meadow and woodland, offering both recreational space for people and refuges for wildlife. More ambitious still are the greenways and ecological corridors designed to connect habitats that have been fractured. These corridors act as lifelines, allowing animals to move between patches, find mates, and recolonize areas where populations have dwindled. Without such links, isolated groups risk genetic decline, their options narrowing with each generation. Perhaps the most famous example of large-scale connectivity is the Yellowstone to Yukon initiative in North America. Spanning thousands of kilometers from the United States into Canada, this project seeks to link protected areas into a continuous chain, enabling species such as wolves, grizzly bears, and elk to move freely along their historic ranges. The idea is simple but profound. Nature does not recognize national borders or property lines, and conservation must therefore transcend them as well. By designing for connectivity, humans can help restore the great movements of wildlife that once shaped ecosystems. Urban areas, too, can become unexpected islands of life. Cities are often seen as biodiversity deserts, but many species adapt to them in surprising ways. Peregrine falcons nest on skyscrapers, treating them as cliffs. Foxes and raccoons prowl suburban streets, turning gardens into feeding grounds. Green roofs and urban parks provide habitats for insects and birds. Yet these urban ecosystems are also fragmented, requiring creative solutions. Wildlife bridges, sometimes humorously dubbed animal commuter lanes, are one such innovation. These structures, often planted with vegetation, allow animals to cross highways safely. In the Netherlands, entire networks of wildlife overpasses and underpasses have been built, enabling deer, boar and even smaller creatures to move without risking their lives in traffic. It is conservation with a dash of whimsy, giving hedgehogs their own safe crossings in a world dominated by cars. The challenge of fragmentation has also inspired the concept of rewilding, restoring landscapes to conditions where nature can once again shape itself. This can mean reintroducing missing species, such as beavers or wolves, or simply allowing land to regenerate into forests or wetlands after agriculture has ceased. Rewilding depends on space and connectivity, for without corridors, newly restored populations remain isolated. In Europe, abandoned farmland has become a canvas for such projects, with wild horses, bison, and lynx reclaiming areas once tilled or grazed. In these cases, human geography is not an obstacle but an enabler, providing the frameworks and policies needed to let wilderness return. Connectivity is as much about time as it is about space. Seasonal migrations of birds, fish and mammals require pathways that span vast distances. Salmon, for instance, must swim upstream from the ocean to spawn, a journey now blocked in many places by dams. Efforts to build fish ladders and remove obsolete barriers are attempts to restore these ancient connections. Migratory birds rely on wetlands and stopover sites along their flyways, many of which have been drained or developed. Protecting these stepping stones is essential, for without them the chain of migration collapses. What is striking is how often small interventions can make large differences. A restored hedgerow can link two woodland fragments for butterflies and birds. A culvert modified to allow amphibians safe passage can prevent local declines. An overpass covered in soil and shrubs may reconnect entire populations of deer or bears. These are not just engineering projects, but bridges of coexistence, acknowledging that human landscapes can be shared rather than dominated. There is a gentle humour in the way these efforts sometimes mirror our own needs. Just as humans require roads, railways and subways to commute safely, so too do other animals need their routes secured. The idea of a hedgehog scurrying along its own designated underpass, or a family of deer taking a wildlife overpass, almost sounds like satire. Yet these measures are serious solutions to serious problems, proving that sometimes the most practical conservation is also the most charming. Human geography, then, is not just about boundaries and barriers, it is about choices. The same ingenuity that lays highways and grids of farmland can also create corridors and networks that stitch ecosystems back together. We are, after all, map makers by nature. With a little imagination, those maps can show not only cities and roads, but also the invisible pathways of migration and survival that other species depend upon. In the end, the challenge is to design landscapes where both people and wildlife can move, feed, and thrive. Corridors, green belts, and rewilded spaces remind us that fragmentation need not be permanent. The land, once broken into pieces, can be reconnected, and perhaps with enough thought, our own commuter lanes can coexist with those of hedgehogs, wolves, and salamanders, each of us travelling along the paths that keep our species alive. Climate has always shifted, but today its pace is quickening, and with it, the living world faces moving goalposts. Temperature bands, the invisible isotherms that once defined comfortable ranges for species, are sliding toward the poles and upward in elevation. What once was a stable backdrop has become a treadmill, and species must run to keep up. For some, this means expanding into new territories. For others, it means retreat, compression, or even disappearance. Geography is being redrawn not by tectonics or sea level, but by degrees Celsius. One of the clearest signs of this shift can be seen in alpine regions. Mountains have long been refugees of cool conditions, their slopes offering vertical gradients where species can climb or descend in tune with climate. But as warming accelerates, alpine tree lines creep higher. Trees colonize meadows that once belonged to wildflowers and shrubs. The squeeze comes at the summit, where there is no further refuge. Plants and animals adapted to thin air and cold soils find themselves with nowhere else to go, trapped at the top of the world. Picas, small mammals known for storing hay in rocky crevices, are already disappearing from parts of their former range in North America, unable to find cool enough conditions as summer's heat. Coral reefs tell another story, this time underwater. Corals live in symbiosis with algae that provide them food through photosynthesis. But these partnerships are fragile. When waters warm beyond tolerance, corals expel their algae, turning ghostly white in a process known as bleaching. Some reefs recover if temperatures fall quickly, others do not. Around the tropics, mass bleaching events have become more frequent, stressing ecosystems that are already fragile. Yet there are glimmers of resilience. Certain reefs, often in areas of upwelling or unusual currents, remain relatively cool. These may serve as refugeia, safe havens where corals persist despite global warming. Protecting such spots is like safeguarding living arcs, holding biodiversity against the storm of change. The consequences are not limited to where species live, but also to when they act. Phenology, the timing of seasonal events like flowering, migration, or breeding, is shifting. Plants bloom earlier in spring, birds arrive sooner from migration, and insects emerge ahead of schedule. When these shifts fall out of sync, mismatches occur. A bird may return to find that the insects it depends on have already peaked, leaving its chicks underfed. Pollinators may arrive too late to benefit from flowers that have already wilted. Timing, once synchronized by stable climates, is becoming a roll of the dice. For species finely tuned to narrow windows of opportunity, even small mismatches ripple into survival challenges. Geography complicates the story further. Coastal species are squeezed not only by warming but by rising seas. Salt marshes, mangroves, and tidal flats can migrate inland only if space exists. Where seawalls and cities block their retreat, they drown. On islands, sea turtles lay eggs on beaches that are shrinking year by year, while seabirds lose nesting grounds to storm surges. Elevational gradients provide escape routes for some, but for low-lying ecosystems, options are limited. Despite the grimness, adaptation windows remain. Topographic diversity creates micro-refugeia, small pockets where local conditions buffer against broader climate trends. A shaded ravine, a north-facing slope, or a spring-fed wetland may stay cooler or wetter than the surrounding landscape. Such microhabitats allow species to persist even as the wider region grows inhospitable. In mountains, this diversity of slopes and aspects means that species may shift sideways rather than always upward, moving into microclimates that mimic the conditions they once knew. Conservation increasingly focuses on protecting these varied terrains, not only the largest expanses but the small wrinkles in the land where life can take shelter. Some species are proving unexpectedly flexible. Certain butterflies in Europe have extended their ranges northward by hundreds of kilometers in just a few decades. Fish once restricted to warmer waters are appearing in new northern seas, altering entire food webs. In cities, birds and mammals adjust breeding seasons and behaviors with surprising speed. These shifts hint at the capacity of life to respond, though not all species are equally nimble. Long-lived plants, for example, cannot relocate in a single generation. Their survival depends on seeds finding new ground, and often humans must assist with corridors or deliberate plantings. Climate change also tests ecosystems as wholes. A forest may persist in name while its composition shifts dramatically. Boreal forests, for instance, may not vanish outright, but could be transformed as spruce give way to deciduous trees better suited to warmth. Grasslands may turn shrubbier, wetlands may dry, and tundra may green. Each transformation affects not only plants, but also the animals, fungi, and microbes tied to them. Ecosystems under shifting isotherms are like orchestras where instruments change mid-performance. The melody continues, but the tune is no longer the same. Humans too are caught in these shifts. Fisheries that once relied on predictable stocks find species moving poleward. Farmers adapt planting calendars as frosts retreat earlier. Alpine communities see both opportunity and loss, longer growing seasons but shrinking snowpacks. The changes are not just ecological, but cultural, rewriting relationships between people and the landscapes they inhabit. The role of conservation is evolving in response. Where once the goal was to preserve static habitats, the focus now is on fostering mobility and resilience. Corridors allow species to track their climates across fragmented landscapes. Protecting elevational gradients ensures escape routes for mountain species. Safeguarding cooler reefs and wetlands prioritizes the refugeia that may carry life through turbulent centuries. The aim is not to freeze nature in place, but to give it room and pathways to move. At the same time, there is value in remembering that species have faced climate swings before. The ice ages reshaped continents repeatedly, and life endured by retreating into refugia and recolonizing when conditions eased. The difference now is speed. Past changes unfolded over thousands of years. Today they race ahead within decades. Whether species can adapt quickly enough is the defining question. The moving goalposts of climate remind us that stability is an illusion. Life is fluid, and geography shifts not only through mountains rising or rivers meandering, but also through invisible bands of temperature migrating across the map. Some species will chase those bands, others will cling in sheltered niches, and still others will fade. What remains is the reminder that the Earth is not static. It breathes, warms, cools, and changes course. For biodiversity, the challenge is not simply to endure, but to flow with those changes, to find new balance under new skies. And for humans, the task is to understand that our maps too must be redrawn, not only of land and water, but of the living ranges that depend upon them. Conservation once focused on drawing lines around special places, parks, reserves, and sanctuaries set aside to protect the rare and the beautiful. These efforts saved countless species and landscapes, but the world is more dynamic than a boundary on a map. Rivers shift course, fire sweeps through woodlands, seas rise and fall, and species move with climate and season. Protecting isolated fragments without considering the larger processes that sustain them is like safeguarding a single gear while ignoring the rest of the clock. Today the emphasis is shifting from protecting static places to protecting the flows, connections, and cycles that give life its resilience. One of the most striking examples of this broader vision is found in the oceans. Marine protected areas, or MPAs, were once scattered like dots across the map, each valuable but often too small or too isolated to safeguard the full sweep of marine life. Now, networks of MPAS are being designed with connectivity in mind. Fish do not stay within neat park boundaries, nor do currents obey human lines. By spacing protected areas like stepping stones, scientists ensure that larvae and juvenile fish can disperse between them, creating resilience across entire seascapes. The Great Barrier Reef Marine Park, for instance, is zoned in a way that balances human use with biodiversity needs, preserving not only coral outcrops, but also the processes of spawning, dispersal, and migration. The result is less like a locked box and more like a flowing system, resilient precisely because of its openness. On land, the same principles apply. Rather than seeing conservation as islands of safety in a sea of development, planners now think in terms of networks and representativeness. Protecting only one forest or one wetland is not enough if it fails to capture the variety of habitats and processes that sustain life. The idea of representativeness is simple but profound. Conservation must reflect the full spectrum of ecosystems, from coastal mangroves to alpine tundra, so that the ecological fabric remains intact. Without this breadth, crucial processes, migration, nutrient cycling, pollination, begin to unravel. Island ecosystems provide another lesson in process-focused stewardship. Isolated by oceans, islands are laboratories of evolution but also highly vulnerable. Many have lost species to invasive predators like rats, cats, or snakes, introduced inadvertently by humans. Modern conservation recognizes that protecting island biodiversity is less about fencing off reserves and more about securing the processes that maintain balance. Biosecurity, preventing invasive species from arriving in the first place, has become as important as preserving habitat. In New Zealand, rigorous quarantine measures protect fragile island sanctuaries, where native birds like the kiwi or kakapo can thrive only if predators remain absent. Here, conservation is not just a static defence, but a continuous active process of vigilance. Thinking in terms of processes also demands patience. Landscapes operate on timescales far longer than human lifetimes. A forest may take centuries to recover its full complexity after logging. Coral reefs may need decades of protection to regrow after bleaching. River systems, when reconnected to floodplains, restore fertility gradually, as sediments accumulate year after year. Conservation that aims to protect processes must embrace this slowness, accepting that true results may unfold not in election cycles or funding periods, but across generations. Stewardship becomes a long, quiet commitment, more akin to tending a garden than finishing a project. Fire management illustrates this perfectly. In many ecosystems, from Australian eucalyptus forests to South African fynbos, fire is not an anomaly but a necessary process. Suppressing all fires leads to dangerous build-ups of fuel and eventual megafires, while carefully managed burns maintain diversity and prevent catastrophe. Conservation here is about guiding a process rather than preserving a snapshot. By aligning with the natural rhythms of disturbance and renewal, these landscapes remain healthy, dynamic, and richly diverse. The language of process-based conservation also reshapes how humans view their role. Instead of treating nature as fragile porcelain to be locked away, it emphasizes resilience. Ecosystems are not static. They pulse, shift, and adapt. Protecting them means respecting those movements and designing with them, not against them. Wetlands need floods, grasslands need grazers, coasts need shifting sands. Trying to hold nature still is both futile and harmful. Supporting its natural dynamism is what keeps it alive. Hope lies in seeing how adaptable this perspective can be. In urban areas, for example, conservation may focus on green corridors that let pollinators move between parks, or on restoring wetlands that buffer storm surges and filter water. These efforts do not create pristine wilderness, but they preserve processes, pollination, filtration, resilience, that benefit both humans and wildlife. Cities, once thought of as biodiversity deserts, can become part of the larger fabric when viewed through this lens. Even in heavily altered landscapes, conservation can lean on processes to rebuild. Rewilding projects in Europe, for instance, focus less on restoring exact historical conditions and more on reinstating ecological roles. Large herbivores like bison and wild horses are reintroduced not simply for their own sake, but because their grazing patterns keep grasslands open, supporting a cascade of other species. Beavers, too, are returning to rivers, their dams slowing water, creating wetlands, and recharging aquifers. The animals are not just individuals to protect, but actors who bring back entire ecological dynamics. Marine systems, again, highlight the importance of scale. Protecting a single reef from fishing pressure does little if warming seas bleach corals across the region. But by safeguarding networks, maintaining water quality, and reducing other stresses, conservation can give reefs breathing space, windows of opportunity to adapt and recover. It is not a guarantee of permanence, but a patient investment in resilience. In the end, conservation by landscape is a philosophy of humility. It acknowledges that humans cannot dictate every detail of ecosystems, but can safeguard the conditions under which they function. It shifts the focus from drawing lines on maps to keeping rivers flowing, fires burning at their natural rhythm, seas replenished with larvae, and species free to move where they must. It is slower, softer work, more about continuity than control, and in that slowness there is a calming cadence. Protecting processes requires trust. Trust that forests will regrow, that wetlands will filter, that animals will recolonize when given pathways. It asks us to think beyond urgency into patience, to accept that our role is not to command but to accompany. In this way, conservation becomes not a battle against loss, but a partnership with time, allowing landscapes to keep their quiet memory alive. So, whether it is a fish drifting from one marine reserve to another, a seed carried into restored soil, or a bird flying through a reconnected corridor, the message is the same. Life is not static, and neither should be our protection of it. By safeguarding processes instead of snapshots, we honour the restless, renewing nature of Earth itself. And perhaps, in that long view, we find a kind of peace, knowing that our guardianship is not about freezing the world in place, but ensuring that its ancient rhythms can continue to flow, steady and enduring, far beyond our own fleeting span. From the first stirring of continents to the present weave of forests, deserts, rivers and seas, one truth runs clear. Life has always followed the lay of the land. The mountains that rose from tectonic restlessness became cradles of rainforests on one slope and drylands on the other. Rivers carved not only valleys but entire genealogies of fish and amphibians. Even soils, silent, unassuming, decided which plants could endure and which could never take root. Geography is not a backdrop. It is the quiet author of possibility, the stage upon which evolution has played its endless improvisations. Through these chapters we've wandered from icy tundras to coral reefs, from deserts blooming after rare rains to deltas rich with shifting fertility. In every place the same pattern revealed itself. Landscapes shape biodiversity not by accident but by design, channeling energy, nutrients and opportunity. Mountains create sky islands, deserts test resilience, monsoons set the tempo of abundance, and fire resets the stage for renewal. Even the hidden worlds underground, cast caves, aquifers and nutrient trickles through stone, prove that life listens to every contour of the earth. What makes this story so compelling is its pace. Geological forces move at the rhythm of centuries and millennia. Mountains rise slowly, rivers shift course over lifetimes, glaciers advance and retreat with patient inevitability. And yet, within these slow arcs, life is astonishingly quick to respond. A new volcanic island emerges, and in a blink of evolutionary time birds, insects and plants arrive, experimenting with niches. A floodplain changes course, and fish, birds, and mammals adjust with a precision honed over countless generations. Deep time writes the stage directions, but life never stops rehearsing and performing in real time. Today, though, those natural tempos are being nudged by human choices. Roads and cities carve new barriers, climate change pushes isotherms at unnatural speeds, and species find themselves sprinting against a shifting backdrop. The lesson from deep time is not despair, but perspective. Life has endured upheavals before, often by retreating into refuges and then radiating outward again. Our role now is to soften the pace of change where we can, and to leave space for those ancient processes to keep working. Conservation is no longer only about preserving static places, but about protecting the flows, rivers connecting wetlands, corridors linking forests, microclimates shielding species from the blunt edge of warming. It's about respecting the dynamism that has always defined life on Earth. And so, this journey returns to you, listening now as evening settles or as night deepens around you. I want to thank you again for joining the Sleepy Geographer. It's a privilege to share these wanderings through landscapes and lives, knowing they may be the final words you hear before drifting into rest. If you'd like, I'd love to know where you're listening from tonight and what time it is there. The constellation of viewers, from cities, villages, coastlines and mountains, feels in its own way like a map of the very connections we've been tracing. Thank you too to those who have subscribed already, and to those considering it. Your support keeps these calm explorations flowing. If tonight's video helped you settle, unwind, or sparked even a small moment of wonder, a like and a subscription are gentle but meaningful ways to keep this project alive. As the words soften now, imagine the spacious quiet of the world at rest. Perhaps moonlight lies across a ridge of mountains, pale and silver, casting shadows down the slopes. Perhaps the tide moves in and out beneath a coastal mangrove, breathing slowly as though the ocean itself were asleep. Or perhaps the image is simpler, a valley hushed after rain, soil rich with the promise of renewal, life waiting for its cue. Wherever your thoughts drift, may they carry the calm weight of knowing that the earth, in all its patterns and processes, continues to turn gently beneath you. Rest well, and may the land itself guide your dreams,